If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The cosmic horizon. Why can't we see beyond? Imagine standing on a vast plain that stretches endlessly in all directions, yet a dense fog limits your vision to only a few miles ahead. You can sense the enormity surrounding you, but your eyes are restricted to what the fog allows. This analogy encapsulates our position in the universe. The observable universe acts as this metaphorical fog, drawing a boundary around the cosmos we can perceive, while hiding whatever lies beyond. But why does this limit exist? What governs the edge of our cosmic view? The answer lies in the fundamental nature of light and the speed at which it travels. Light, as you may know, moves at a staggering pace, approximately 186,000 miles per second. Despite its immense speed, it is finite, and so is the time that light has had to reach us since the birth of the universe approximately 13.8 billion years ago. The furthest light we can detect today began its journey near the universe's beginning, traversing an unimaginably vast expanse to reach us. Yet the accelerating expansion of the cosmos complicates this seemingly straightforward relationship. Our observable universe is not defined merely by the age of the cosmos, but by the interplay of light and cosmic inflation. Shortly after the Big Bang, the universe underwent a rapid expansion, inflating exponentially in a fraction of a second. This event stretched space-time itself, causing regions of the universe to move away from one another faster than the speed of light. A phenomenon allowed not because objects themselves exceed light speed, but because the fabric of space-time does. This rapid inflation set the stage for our cosmic horizon, the maximum distance light has had time to travel since the universe's birth. Today, that horizon measures about 93 billion light-years across, far larger than the universe's age in years might suggest. This apparent paradox stems from the fact that while light travels at a constant speed, space itself has expanded significantly during that time, carrying galaxies far beyond their original locations. Yet, the observable universe represents only a fraction of the entire cosmos. Beyond this horizon lies a realm forever hidden, not because it doesn't exist, but because its light will never reach us. As the universe continues its relentless expansion, the gap between us and these far-off regions grows larger. Every moment that passes increases the distance galaxies are carried away, like driftwood on an ever-widening ocean current. The further these galaxies move, the more light struggles to bridge the gap. The concept of a cosmic horizon challenges the very way we think about limits. For centuries, human exploration was driven by a desire to find the edges of the Earth and cross uncharted waters. In cosmology, the edges aren't physical barriers but dictated by the laws of physics themselves. What lies beyond the horizon might be galaxies similar to those within our view, or entirely different cosmic structures, shaped by exotic conditions we can scarcely imagine. Complicating this picture further is the role of time. When we observe distant galaxies, we're not seeing them as they are today, but as they were billions of years ago. Light from these objects has traveled vast distances, carrying information frozen in time. This means our observable universe is as much a time machine as it is a spatial boundary. What we see today might no longer exist in the same form, and what exists now beyond the horizon may never become visible, even with infinite technological advancements. This limit is not just a boundary of observation. It also represents a barrier to understanding. The farther we look, the more the universe challenges our knowledge of physics and cosmology. Galaxies at the edge of our view move away so rapidly due to cosmic expansion that their light becomes redshifted, stretched to wavelengths too long for human eyes or even many instruments to detect. This cosmic redshift is a vivid reminder that the universe is not static but dynamic and ever-evolving. But what are the philosophical implications of this boundary? Does the existence of an observable universe imply that the cosmos itself has an end? Most cosmologists argue no. The observable universe is merely our slice of a much larger, potentially infinite whole. To use the earlier analogy, the fog obscures not a wall, but an endless plain. Beyond the horizon could lie more galaxies, stars, and planets, perhaps an infinite number of them. This raises profound questions. If the universe is infinite, does it mean there are infinite copies of everything we know, including alternate versions of ourselves? Or is the cosmos beyond simply a continuation of the familiar, bound by the same laws of physics, but unreachable? These questions remain unanswered, as our tools, though sophisticated, are inherently bound by the limits of observation. However, this hasn't deterred theorists from imagining what lies beyond. Some propose that the universe beyond the observable horizon might operate under different physical laws. Others suggest that it is part of a multiverse, a collection of bubble universes, each with its own distinct properties. If true, our observable universe would be a mere drop in an ocean of existence, a single page in an infinite book of creation. The cosmic horizon also teaches us humility. Despite our technological achievements, the universe reminds us of our limitations. We are inhabitants of a small planet orbiting an average star in a galaxy among trillions, all confined within an observable sphere that represents a fraction of reality. Yet, even within this fraction, we've uncovered incredible truths about the universe's origins, structure, and destiny. As technology advances, will we ever peer beyond this horizon? The laws of physics as we understand them suggest not. But as history shows, the human quest for knowledge often defies what once seemed impossible. Perhaps one day, through theoretical breakthroughs or new discoveries, we'll unlock ways to glimpse beyond the observable universe, shedding light on the vast unknown. For now, the cosmic horizon remains a tantalizing frontier. It defines the limit of our perception, yet sparks infinite curiosity. What lies beyond? Could there be other civilizations looking toward their own horizons, wondering the same about us? These mysteries serve as a powerful reminder that the universe, in all its grandeur, is far more than what we see. It is an infinite invitation to wonder. Infinite universe or bubble multiverse. As we push our imaginations beyond the observable universe, we face an astonishing question. Does the cosmos stretch on infinitely, or is it one of countless bubbles floating in a multiverse sea? These two possibilities, an infinite universe or a bubble multiverse, represent some of the most mind-bending ideas in modern cosmology. Each challenges our understanding of reality and hints at possibilities so vast they seem almost impossible to comprehend. To grasp these concepts, we must first explore the idea of an infinite universe. When we think of infinity, our minds often picture endless repetition, a number line stretching in both directions, an ocean without shores, or the night sky extending forever. But applying infinity to the universe brings profound implications. If the cosmos truly has no end, then everything we know, galaxies, stars, planets, and even life itself, may repeat endlessly, with every possible configuration occurring somewhere, sometime, an infinite number of times. This vision of an infinite universe stems from our current understanding of cosmology. Observations suggest that space is flat or nearly flat, meaning it does not curve back on itself like the surface of a sphere. A flat universe could, in principle, extend forever, with no boundaries or edges. If true, this would imply that the regions beyond our observable horizon are simply more of the same, galaxies, stars, and cosmic structures stretching endlessly into the distance. But does infinity mean duplication? The answer lies in probability. In an infinite universe, there are only so many ways particles can arrange themselves. After a certain point, those arrangements must repeat. Somewhere, unimaginably far away, could be a galaxy identical to our Milky Way. On a distant planet in that galaxy, there might be another version of you reading these words. This concept of cosmic doppelgangers is both fascinating and unnerving, hinting that our reality might not be as unique as we believe. Yet, this infinite framework raises questions. If the universe is endless, why does it appear homogeneous, relatively uniform, on large scales? The answer lies in the theory of cosmic inflation. Shortly after the Big Bang, the universe expanded exponentially fast, smoothing out irregularities and creating the vast, flat cosmos we observe today. But inflation doesn't just explain the observable universe. It hints at the existence of regions far beyond our view, each shaped by the same process. Here, the idea of the bubble multiverse comes into play. According to some interpretations of inflation theory, the process that created our universe didn't end uniformly. Instead, inflation could still be happening in other parts of the cosmos, creating pockets or bubbles of space-time. Each bubble would represent a universe unto itself, with its own physical laws, constants, and structures. Our observable universe, then, would be just one bubble in a frothy multiverse, surrounded by countless others. But what separates one bubble from another? The key lies in quantum mechanics. During inflation, quantum fluctuations, tiny random changes at the smallest scales, would have created variations in energy density. These fluctuations seeded the formation of bubbles, each with its own unique conditions. Some bubbles might resemble ours with galaxies, stars, and planets, while others could be radically different, governed by unfamiliar forces or containing no matter at all. If the multiverse theory is correct, it raises the tantalizing possibility that everything we've ever known is but a sliver of reality. Our universe's laws, gravity, electromagnetism, and the behavior of particles might be mere local rules, applying only within our bubble. Other bubbles could operate under entirely different principles, with dimensions beyond the three of space and one of time we experience. These alternate realities could harbor exotic forms of matter, unknown forms of life, or phenomena so strange we lack the language to describe them. But can we prove the existence of a multiverse? This question lies at the cutting edge of science and philosophy. By definition, regions beyond our observable universe are inaccessible to us. They lie outside the reach of light, and thus beyond direct observation. However, some scientists believe the multiverse might leave subtle imprints on our cosmos. For instance, if two bubbles collided in the distant past, the resulting energy might have left traces in the cosmic microwave background, the faint afterglow of the Big Bang. Such evidence remains speculative, but technological advances could change that. Future experiments in particle physics, gravitational wave detection, and cosmology might reveal clues pointing toward the multiverse. Meanwhile, mathematical models continue to expand our understanding of inflation, quantum mechanics, and the potential connections between bubbles. The bubble multiverse also carries profound philosophical implications. If there are countless universes, each with its own laws and histories, then where does that leave us? Are we insignificant specks in an infinite ensemble, or is our existence part of a grander design? These questions touch on the nature of meaning, reality, and our place in the cosmos, forcing us to confront the limits of human understanding. Interestingly, the idea of a multiverse is not new. Ancient philosophers, such as the Greek atomists, speculated about the existence of infinite worlds. These early musings were rooted in intuition rather than science, but they resonate with today's theories. Modern cosmology, armed with mathematics and observation, has given these age-old ideas new life, grounding them in the framework of inflationary theory and quantum physics. Yet, even within the scientific community, the concept of a multiverse remains controversial. Critics argue that without direct evidence, the multiverse is more a philosophical idea than a scientific theory. Others counter that the multiverse, while difficult to test, is a natural consequence of our best models of the universe's origins. In their view, the multiverse isn't an extraordinary claim, it's a logical extension of known physics. As we contemplate the infinite universe and the bubble multiverse, we're reminded of the profound mystery of existence. Whether the cosmos extends forever or consists of countless bubbles, the implications are staggering. In an infinite universe, every possibility exists somewhere. In a multiverse, each bubble represents a unique reality, a new chapter in the story of creation. Both concepts challenge us to think beyond our observable limits, to imagine the unimaginable. Ultimately, the true nature of what lies beyond may forever elude us. But this uncertainty is not a barrier. It's an invitation to explore, to question, and to dream. The cosmos, in all its vastness, is a testament to the power of curiosity and the infinite possibilities that await those who dare to ask what lies beyond. The edge of space-time. Is there a boundary? As we venture deeper into the mysteries of the cosmos, a profound question emerges. Does the universe have an edge? If so, what lies beyond it? If not, how do we conceptualize a space-time that stretches endlessly or folds back on itself in ways our minds struggle to comprehend? The notion of a boundary, or lack thereof, challenges not only the limits of our observation, but also the very fabric of reality itself. To understand the concept of an edge, we must first explore what space-time truly represents. In Einstein's theory of general relativity, space and time are not separate entities, but interconnected dimensions, forming a four-dimensional continuum that bends and warps in response to mass and energy. This dynamic fabric of space-time is what gives rise to gravity and dictates the motion of everything in the cosmos, from planets to light beams. If space-time can bend, does it also end? Our instincts, shaped by a world of finite objects, suggest that all things must have edges. But the universe defies such intuition. Most cosmologists believe the universe has no physical boundary, not in the way a wall might mark the edge of a room. Instead, space-time could be infinite, stretching endlessly in all directions, or finite but unbounded, curving back on itself like the surface of a sphere. This second possibility, a finite but unbounded universe, deserves closer examination. Imagine standing on the surface of a sphere, such as Earth. From your perspective, there are no edges. You can walk in any direction indefinitely without encountering a boundary. Yet the surface is finite. It has a definite area. In the same way, the universe could be finite in size while lacking edges, looping back on itself in dimensions we cannot directly perceive. To explore whether space-time has an edge, we also need to consider the observable universe. As discussed earlier, our cosmic view is limited by the speed of light and the universe's age. The observable universe is not a physical boundary, but a horizon, a spherical region defined by the farthest distances light has traveled since the Big Bang. Beyond this horizon lies the unobservable cosmos, which may or may not stretch infinitely. If space-time is infinite, what does that mean for the structure of the cosmos? An infinite universe would contain an infinite amount of matter, energy, and space, potentially arranged in patterns that repeat endlessly. Such a scenario aligns with the idea of a flat universe, suggested by observations of the cosmic microwave background and the distribution of galaxies. A flat space-time, according to geometry, can extend forever, with no edges or limits. But even if the universe is infinite, could there still be a boundary of sorts, a region where familiar physics breaks down? Some theories suggest that beyond our observable universe, the laws of nature might change. Constants like the speed of light or the strength of gravity could vary, creating exotic regions where reality functions differently. These cosmic domains might be separated from our own by transition zones, conceptual boundaries where one set of laws gives way to another. The idea of such boundaries touches on the concept of cosmic inflation. As discussed earlier, inflation proposes that the universe expanded exponentially in its earliest moments, creating vast regions of space-time. If inflation continues in some areas while stopping in others, the universe could consist of separate domains, each with its own properties. These domains might be disconnected from one another, making their boundaries impossible to cross. In a finite but unbounded universe, what lies beyond the curvature? If space loops back on itself, traveling far enough in one direction could, in theory, bring you back to your starting point. This raises fascinating questions about the nature of distance and direction. Is beyond a meaningful concept if every path eventually circles back? And if space is curved, could it connect in unexpected ways, allowing shortcuts or wormholes to other parts of the cosmos? The edge of space-time also intersects with the question of time itself. Just as the universe may lack spatial boundaries, it may also be timeless in some sense, with no clear beginning or end. While the Big Bang marks the start of the observable universe, some theories suggest it was not the true origin of existence. Instead, the Big Bang could be a localized event in a much larger, eternal cosmos, a moment of transformation rather than creation. If space-time does have an edge, could it be crossed? In science fiction, the end of the universe often takes the form of a physical barrier, a shimmering wall, or an energy field. In reality, any edge of space-time would likely be far stranger. One possibility is that the universe ends in a singularity, a region where space-time curvature becomes infinite and the laws of physics break down. Singularities already exist within black holes, where matter is crushed to infinite density. Could the universe itself have a singular edge, an ultimate boundary beyond which nothing exists? Another possibility is that the edge of space-time connects to something else entirely, a higher dimensional realm or another universe. In theories like string theory and M-theory, the universe we perceive is a brain floating in a higher dimensional space. The edge of our brain might lead to other brains, each representing a separate universe with its own dimensions and properties. These ideas, though speculative, expand our understanding of what a boundary could mean. But how can we test such theories? Observing the edge of space-time is inherently challenging, as light and information cannot travel from beyond the observable universe. However, scientists can search for indirect clues. Anomalies in the cosmic microwave background, gravitational waves, or the distribution of galaxies might hint at unseen structures or transitions. Advanced simulations and mathematical models also help cosmologists explore scenarios that align with observed data. The edge of space-time is not just a scientific mystery, it's a philosophical one. If the universe has no boundary, what does that mean for our place within it? Are we tiny, insignificant beings in an endless void? Or is infinity itself a reflection of the boundless potential of existence? Conversely, if the universe does have an edge, what lies beyond? Does existence give way to non-existence? Or does reality continue in forms we cannot comprehend? These questions remind us of the dual nature of cosmology. It is a science grounded in observation and theory, yet it also touches on the deepest questions of meaning and existence. Whether space-time is infinite, finite, or connected to something beyond, it challenges us to expand our understanding of reality and embrace the vastness of the unknown. Ultimately, the edge of space-time, if it exists, may forever remain a mystery. Yet this mystery is not a limitation. It is an inspiration. It reminds us that the universe is not just a collection of stars and galaxies, but a profound testament to the infinite possibilities of existence. Whatever lies beyond the observable, the journey to understand it is as boundless as the cosmos itself. Cosmic inflation and the unobservable realms. To uncover what lies beyond the observable universe, we must journey back to the earliest moments of existence, an era defined by a phenomenon so profound that it reshaped our cosmos forever: cosmic inflation. This event, occurring within a fraction of a second after the Big Bang, not only expanded space-time exponentially, but also left an indelible mark on the universe's structure. What does inflation tell us about the regions we cannot see? And how does it hint at the unobservable realms beyond our cosmic horizon? To comprehend inflation, imagine the universe as a tiny balloon. Before inflation, this balloon was minuscule, packed with intense energy and unfathomable density. Then, in a moment lasting less than a trillionth of a second, it underwent an explosive expansion, growing exponentially larger. This rapid inflation stretched space-time to scales incomprehensible to the human mind, smoothing out irregularities and setting the stage for the universe we observe today. The theory of inflation solves several puzzles in cosmology. For instance, the universe appears remarkably uniform on large scales, with galaxies and cosmic structures distributed evenly across the sky. Without inflation, such uniformity would be inexplicable, as distant regions of the cosmos would not have had time to interact and exchange energy. Inflation, by stretching these regions, created the homogeneity we see while also explaining the subtle variations that later grew into galaxies and stars. But inflation doesn't stop at explaining our observable universe. It also points to the existence of unobservable realms, regions of space-time so far removed from us that their light will never reach Earth. During inflation, quantum fluctuations, tiny, random changes in energy, were magnified and frozen into the fabric of space-time. These fluctuations created density variations that seeded the formation of galaxies. However, they also produced variations beyond our observable horizon, shaping parts of the universe we can never see. This brings us to one of the most fascinating implications of inflation: the multiverse. According to some interpretations, inflation was not a one-time event confined to our universe. Instead, it may be an ongoing process, creating countless bubble universes in a larger multiverse. In this scenario, our observable universe is just one bubble in a vast, frothy expanse of inflating spacetime. Each bubble represents a separate region of the cosmos, with its own physical laws and properties. The idea of a multiverse reshapes our understanding of reality. If inflation is eternal, new bubbles are constantly forming, each expanding into its own universe. Some of these universes might resemble ours, with galaxies, stars, and life. Others could be radically different, governed by alternate physical laws, or containing dimensions beyond those we perceive. The multiverse would be a cosmic mosaic, a collection of infinite possibilities, each as real as our own. But what separates one bubble from another? The answer lies in quantum mechanics. During inflation, the energy driving the process fluctuates randomly, creating pockets where inflation ends and others where it continues. These pockets become the seeds of individual universes, each with unique properties determined by the conditions in which it formed. The boundaries between these bubbles are not physical walls but transitions in space-time, a concept as abstract as it is profound. If inflation produces a multiverse, what does that mean for the unobservable regions of our own bubble? These areas, though inaccessible to us, could extend infinitely, containing countless galaxies and stars similar to those within our horizon. Alternatively, they might transition into different phases of space-time, with physical laws that deviate subtly or dramatically from those we know. In either case, inflation ensures that our observable universe is just a fraction of the cosmic whole. Inflation also raises questions about the ultimate fate of the universe. As inflationary models suggest, space-time could continue expanding indefinitely, driven by the same forces that fueled its rapid growth in the early moments. This expansion, now attributed to dark energy, pushes galaxies apart at an accelerating rate, ensuring that much of the cosmos will drift forever beyond our view. In the distant future, even the nearest galaxies may become unreachable, leaving observers with a night sky devoid of light. Yet, the unobservable realms may still influence our universe. Quantum entanglement, a phenomenon where particles remain connected regardless of distance, hints that regions beyond our horizon could interact with us in subtle ways. These connections, though speculative, suggest that the cosmos is a unified whole, with its parts intertwined in ways we do not yet understand. Such ideas challenge the notion of isolation, offering a glimpse of a deeper, hidden order. What evidence supports the theory of inflation and its implications for the unobservable cosmos? One key piece is the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB reveals subtle patterns of temperature and polarization that align precisely with predictions from inflationary models. These patterns, imprinted on the universe when it was just 380,000 years old, are a snapshot of the conditions inflation created, offering a window into the earliest moments of existence. Further evidence comes from the distribution of galaxies and large-scale structures in the universe. Observations show that matter clusters in a way consistent with the density fluctuations produced by inflation. These patterns, amplified over billions of years by gravity, reflect the quantum seed sown during the universe's rapid expansion. Despite its successes, inflation remains a theory, and many questions linger. For example, what triggered inflation, and what caused it to end in our region? Is it truly eternal, or did it only occur in a finite patch of space-time? These mysteries drive ongoing research as scientists refine their models and search for new evidence. Technological advancements may one day expand our understanding of inflation and the unobservable realms. Next-generation telescopes, gravitational wave detectors, and particle accelerators could reveal clues about the universe's earliest moments, providing insights into the mechanisms of inflation and the possible existence of other universes. The implications of inflation extend far beyond science. They challenge our perception of reality, pushing the boundaries of imagination and forcing us to confront the limits of human understanding. If the unobservable realms exist, they remind us that the cosmos is far grander than what we see, a vast, infinite stage where every possibility plays out, from the familiar to the unimaginable. Ultimately, inflation offers a profound lesson about the nature of existence. It reveals that the universe is not static or confined, but dynamic and boundless, shaped by forces that transcend our comprehension. Whether we ever fully understand these forces or glimpse the unobservable realms, their existence inspires awe, curiosity, and a deeper appreciation for the infinite cosmos we call home. Dark energy's role in hiding the unknown. Imagine a cosmic force so mysterious and powerful that it defies explanation, shaping the destiny of the universe and obscuring regions of space from our view forever. This enigmatic force is dark energy, and it has become one of the greatest puzzles in modern cosmology. But what is dark energy, and how does it contribute to hiding the unobservable regions of the cosmos? To answer these questions, we must unravel its influence on the universe's expansion and explore how it transforms our understanding of what lies beyond the observable horizon. The story of dark energy begins with the discovery that the universe is expanding. In the early 20th century, astronomer Edwin Hubble observed that distant galaxies are moving away from us, their light stretched to longer, redder wavelengths. This redshift revealed that the fabric of space itself is stretching, carrying galaxies apart. Initially, scientists believed that this expansion would slow over time due to the gravitational pull of matter. But in 1998, two independent teams of astronomers studying distant supernovae made a groundbreaking discovery. The universe's expansion is not slowing down, it is accelerating. This revelation upended our understanding of cosmic dynamics and pointed to the existence of an unknown force driving this acceleration. That force was named dark energy. Dark energy is not like the matter or energy we encounter in everyday life. It does not emit, absorb, or reflect light, making it invisible and elusive. Its effects, however, are profound. Dark energy acts as a repulsive force, counteracting gravity and pushing the universe's contents apart. This repulsion grows stronger as the universe expands, dominating its large-scale behavior and shaping its ultimate fate. One of dark energy's most striking consequences is its role in hiding parts of the universe from view. As space expands, distant galaxies move away from us at ever-increasing speeds. At a certain point, these galaxies recede faster than the speed of light. Not because they are moving through space at such speeds, but because the space between us and them is expanding so rapidly. When this happens, their light can no longer reach us, and they vanish beyond our observable horizon. This phenomenon means that the observable universe is shrinking in a relative sense. While the total amount of space and galaxies in existence remains vast, the regions accessible to our observation are dwindling. With every passing moment, more galaxies are carried beyond the reach of our instruments, their light stretched to wavelengths too long to detect. Eventually, they will disappear entirely, leaving behind a universe increasingly empty and isolated. The accelerating expansion caused by dark energy raises profound questions about the future. If this trend continues, the cosmos will enter an era known as the Big Freeze or heat death. In this scenario, galaxies will drift so far apart that they become invisible to one another. Stars will burn out, and black holes will slowly evaporate through Hawking radiation. What remains will be a dark, cold expanse, with no structure or activity, a far cry from the vibrant universe we see today. Dark energy also deepens the mystery of what lies beyond the observable universe. As regions of space recede beyond our horizon, they become forever inaccessible to us. Yet, they continue to exist, following their own paths and evolving independently of what we can observe. This creates a profound asymmetry. We know these regions are there, but we can never explore or interact with them, even in principle. But what is dark energy, really? Scientists have proposed several explanations, though none are definitive. One possibility is that dark energy represents a property of spacetime itself, an inherent cosmological constant first proposed by Albert Einstein. According to this view, dark energy is a constant energy density filling all of space, causing it to expand. Another theory suggests that dark energy is a dynamic field, similar to the forces responsible for inflation in the early universe. This quintessence model envisions dark energy as a changing entity whose properties evolve over time. If true, this could mean that the universe's acceleration might not last forever. It could slow, stop, or even reverse, leading to a cosmic contraction or big crunch. Dark energy might also hint at physics beyond our current understanding. Some scientists speculate that it could be tied to extra dimensions, as proposed in string theory, or to the vacuum energy of quantum fields. Others suggest that our understanding of gravity itself might be incomplete, and that a new theory of spacetime could explain the observed acceleration without invoking dark energy at all. Despite its mystery, dark energy leaves detectable imprints on the cosmos. One key source of evidence is the cosmic microwave background (CMB), the faint afterglow of the Big Bang. Dark energy influences the distribution of matter and the large-scale structure of the universe, which are reflected in the patterns of the CMB. Observations of galaxy clusters, supernovae, and gravitational lensing also provide clues about dark energy's effects. Future advancements in technology and observation may bring us closer to understanding dark energy. Space telescopes like the James Webb Space Telescope and upcoming missions such as the Euclid satellite and the Nancy Grace Roman Space Telescope aim to study the universe's expansion in unprecedented detail. By analyzing the distribution of galaxies, the behavior of supernovae, and the properties of dark matter, these instruments could shed light on dark energy's nature and origins. Yet, even as we uncover more about dark energy, its implications force us to confront profound philosophical questions. What does it mean to exist in a universe where so much is hidden, where vast regions are forever beyond our reach? How do we reconcile our finite perspective with the infinite expanse of the cosmos? And what role do we, as observers, play in this ever-evolving tapestry of space and time? Dark energy reminds us of the limits of human understanding and the boundless possibilities of discovery. It is a force that reshapes our universe, revealing the intricate interplay between the seen and unseen, the known and the unknown. As we strive to unravel its mysteries, we are reminded of the grandeur of the cosmos and our place within it, a fleeting moment in an infinite expanse, illuminated by curiosity and wonder. Have you ever looked at the sky and felt the desire to understand your place in the universe? On Beyond the Stars, every video is a window to infinity, a journey to connect you with the mystery and beauty of the cosmos. Subscribing to the channel is more than clicking a button. It's joining a movement to spread knowledge and inspire others to look at the stars with hope and curiosity. Be the light that guides others to discover the wonders of the universe. Subscribe, and let's explore the unknown together. The cosmic web and hidden structures. When you gaze up at the night sky, the vast tapestry of stars and galaxies appears random, scattered without rhyme or reason. Yet beyond this seemingly chaotic display lies an intricate structure, a vast cosmic web of interconnected galaxies, dark matter, and invisible forces shaping the universe. But what does this web reveal about the hidden structures of the cosmos? And could it offer clues about the unseen regions beyond our observable universe? The concept of the cosmic web emerged from decades of astronomical observations and simulations. Galaxies, while appearing randomly distributed on small scales, actually form part of a larger framework, a sprawling network of filaments and voids spanning billions of light years. These filaments, composed primarily of dark matter, act as the scaffolding of the universe, guiding the formation of galaxies and clusters. Dark matter is the invisible backbone of the cosmic web. Unlike the ordinary matter we encounter daily, dark matter does not emit, absorb, or reflect light. Its presence is inferred from its gravitational effects, such as the way it holds galaxies together and bends light in a phenomenon known as gravitational lensing. Dark matter dominates the mass of the universe, outnumbering ordinary matter by a factor of about 5 to 1, and it is essential to understanding the universe's structure. At the intersections of the cosmic web's filaments lie galaxy clusters, massive groupings of hundreds or thousands of galaxies bound together by gravity. These clusters are the densest regions of the cosmic web, glowing brightly in X-ray wavelengths due to the hot gas trapped within them. Between the filaments, however, lie vast voids, enormous regions of empty space, spanning tens or even hundreds of millions of light years, with very few galaxies. The existence of these voids is as fascinating as the filaments themselves. They represent regions where the density of matter is far lower than the cosmic average. In a sense, these voids are windows into the universe's early history, as their emptiness reflects the initial conditions of the cosmos after inflation. But could these voids also hold hidden secrets? Some theories suggest that they might contain exotic forms of matter or provide clues about the fundamental nature of space-time. Mapping the cosmic web requires cutting-edge technology and techniques. Astronomers use surveys of galaxies, such as those conducted by the Sloan Digital Sky Survey, SDSS, to create detailed maps of the universe's large-scale structure. By measuring the positions and redshifts of millions of galaxies, they reveal the web's filaments and voids, painting a picture of the universe's vast interconnectedness. One of the most intriguing aspects of the cosmic web is its role in hiding unseen structures. While galaxies and galaxy clusters are the most visible components of the web, the filaments themselves are largely invisible, composed primarily of dark matter and diffuse gas. This missing matter is incredibly difficult to detect, as it emits very little radiation. However, astronomers have begun to uncover it using innovative techniques, such as observing the slight distortions in light caused by gravitational lensing or detecting faint X-rays from hot gas in the filaments. These hidden structures may also extend beyond our observable universe. If the cosmic web continues indefinitely, it could connect unseen regions of the cosmos, forming a network that spans not just our observable horizon, but the entirety of space-time. In this view, the web is a universal framework, linking galaxies, clusters, and voids in a vast, interconnected whole. The cosmic web also raises fascinating questions about the relationship between dark matter and dark energy. While dark matter acts as the scaffolding of the web, pulling galaxies together, dark energy drives the universe's expansion, pushing them apart. This tension between attraction and repulsion shapes the evolution of the web over time. As dark energy accelerates the universe's expansion, the filaments of the web are stretched and thinned, and the connections between clusters weaken. But could the cosmic web provide evidence of phenomena even more exotic than dark matter and dark energy? Some theories propose that the web might contain cosmic strings, narrow, high-energy defects in space-time left over from the universe's earliest moments. These strings, if they exist, would create unique gravitational effects, distorting the web and leaving detectable imprints in the cosmic microwave background. The web's hidden structures also challenge our understanding of gravity and the laws of physics. Modified gravity theories, such as MOND, modified Newtonian dynamics, attempt to explain the behavior of the cosmic web without invoking dark matter. These theories remain controversial, but highlight the need for a deeper understanding of how the universe's large-scale structure forms and evolves. One of the most exciting frontiers in studying the cosmic web is the search for its faintest components. Recent observations have detected the missing baryons of the universe, ordinary matter that had previously eluded detection, within the filaments of the web. These baryons, in the form of hot, diffuse gas, provide crucial insights into the distribution of matter and the processes driving galaxy formation. As technology advances, our ability to map and study the cosmic web will continue to grow. Next-generation telescopes, such as the Vera C. Rubin Observatory and the Square Kilometer Array, will provide unprecedented views of the web's structure, revealing its most intricate details. Meanwhile, simulations run on powerful supercomputers, such as the Illustris and Millennium simulations, will refine our understanding of how the web forms and evolves over time. The cosmic web is more than just a structure. It is a key to understanding the universe's hidden realms. Its filaments and voids represent the interplay of visible and invisible forces, the seen and the unseen. As we probe deeper into its mysteries, we are not just mapping the cosmos. We are uncovering the fundamental principles that govern existence. Ultimately, the cosmic web reminds us of the universe's complexity and beauty. It is a vast, interconnected network, stretching across space and time, linking galaxies and voids in a cosmic dance. Whether it extends beyond our observable horizon or serves as a bridge to even greater mysteries, the web is a testament to the boundless possibilities of discovery, a reminder that the universe, in all its grandeur, is more interconnected than we could ever imagine. Parallel universes, theory or reality. As we delve into the profound mysteries of the cosmos, one question stands out. Could there be other universes beyond our own? The idea of parallel universes, realities that exist alongside ours but are hidden from view, has captivated human imagination for centuries. Once the domain of philosophy and science fiction, this concept has now found a place in cutting-edge physics and cosmology. But are parallel universes merely theoretical constructs? Or could they be as real as the stars we see in the night sky? The notion of parallel universes arises from several scientific frameworks, each offering a different perspective on the nature of reality. One of the most compelling sources is quantum mechanics, the branch of physics that describes the behavior of particles at the smallest scales. In the quantum world, particles do not have fixed states. Instead, they exist in a superposition of possibilities until observed. For example, an electron can be in multiple places at once, and only when measured does it choose a position. This probabilistic nature of quantum mechanics led physicist Hugh Everett to propose the many-worlds interpretation in the 1950s. According to this interpretation, every quantum event causes the universe to split into multiple branches, each representing a different outcome. In this view, parallel universes are constantly being created, with every decision, every particle interaction, spawning a new reality. In one universe, you might have chosen coffee over tea this morning. In another, the opposite. These countless branches form an ever-expanding multiverse, a vast collection of alternate realities. While the many-worlds interpretation remains controversial, it is not the only path to parallel universes. The theory of cosmic inflation, discussed earlier, also provides a foundation for the multiverse concept. Inflation proposes that our universe expanded rapidly after the Big Bang, but this process may not have been uniform. Instead, it could have created countless bubble universes, each separated by vast stretches of inflating space-time. These bubbles could have their own laws of physics, constants, and dimensions, making them fundamentally different from our own universe. String theory, another major framework in modern physics, adds yet another layer to the multiverse hypothesis. According to string theory, the fundamental building blocks of reality are not particles but tiny, vibrating strings. These strings operate in a universe with more than 3 spatial dimensions, perhaps as many as 11. In this context, parallel universes could exist in these extra dimensions, folded so tightly that they are imperceptible to us. Alternatively, our universe might be a brain floating in a higher dimensional space, with other brains representing parallel realities. The existence of parallel universes raises profound questions about the nature of existence. If they are real, how many are there? Are they infinite, each containing variations of our universe? Or are they finite, with a limited number of possibilities? Could some universes harbor life, while others are barren? And what does it mean for our sense of identity if versions of ourselves exist elsewhere, making different choices and living alternate lives? Testing the existence of parallel universes is an immense challenge, as they are, by definition, beyond direct observation. However, scientists have proposed several ways to search for indirect evidence. For example, if our universe is part of a multiverse, collisions between bubble universes could leave imprints in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Anomalies or patterns in the CMB might hint at interactions with other universes in the distant past. Gravitational waves, ripples in space-time caused by massive cosmic events, could also provide clues. If parallel universes exist, they might influence the behavior of these waves, creating detectable signatures. Similarly, certain quantum experiments could reveal hints of alternate realities by detecting deviations from expected outcomes. One of the most intriguing ideas is the potential role of black holes in connecting universes. According to some theories, black holes could serve as gateways to other dimensions or parallel realities. When matter falls into a black hole, it is thought to be compressed to a singularity, a point of infinite density where the known laws of physics break down. However, some physicists propose that this matter might be transported to another universe, creating a white hole on the other side, where matter is ejected. Despite these tantalizing possibilities, the concept of parallel universes is not without its skeptics. Critics argue that the multiverse hypothesis, while mathematically consistent, is inherently untestable and therefore falls outside the realm of empirical science. If parallel universes cannot be observed or measured, can their existence ever be confirmed, or are they simply philosophical constructs? Yet, even skeptics acknowledge the value of exploring these ideas. The multiverse hypothesis pushes the boundaries of scientific inquiry, challenging us to think beyond the confines of our observable universe. It also has profound implications for understanding fundamental questions, such as why our universe has the specific properties that allow life to exist. If countless universes exist, each with different laws of physics, then our universe might be one of the few, or the only one, capable of supporting life. This idea, known as the anthropic principle, suggests that the multiverse might explain the apparent fine-tuning of our cosmos. Parallel universes also resonate deeply with human curiosity and imagination. They invite us to ponder questions of identity, possibility, and choice. What if other versions of ourselves are living out alternate lives? What if there are realities where history unfolded differently, where ancient civilizations thrived, or where humanity never emerged? These ideas, while speculative, inspire a sense of wonder and a desire to explore the unknown. As our understanding of physics and cosmology advances, the possibility of parallel universes remains a tantalizing frontier. Whether they are real or remain theoretical, they challenge us to expand our vision of reality and embrace the vastness of existence. The quest to uncover their secrets is not just a scientific endeavor. It is a journey into the deepest mysteries of being, a reminder that the cosmos is far more intricate and extraordinary than we can imagine. Exotic physics beyond the horizon. The universe, vast and mysterious, is governed by laws of physics that seem universal, rules we've meticulously observed and tested in laboratories, star systems, and distant galaxies. Yet, what if these laws, the very foundation of our understanding, are not constant across the cosmos? Could the universe beyond our observable horizon operate under entirely different principles, revealing exotic physics that reshape our understanding of reality? To begin exploring this possibility, we must consider the observable universe itself. Here, physics as we know it reigns supreme. From the subatomic world of quantum mechanics to the large-scale structure of the cosmos governed by general relativity, these laws have been remarkably successful at describing phenomena across an enormous range of scales. But there is no guarantee that these laws apply everywhere in the universe, especially in regions we cannot observe. The possibility of exotic physics arises from the idea that the universe might be far more diverse than it appears. This diversity could stem from the conditions under which different regions of space-time were formed. According to the theory of cosmic inflation, our universe underwent an explosive expansion shortly after the Big Bang, smoothing out irregularities and creating a relatively homogeneous observable universe. However, inflation may not have occurred uniformly everywhere. In some regions, quantum fluctuations during inflation could have led to vastly different conditions, resulting in pockets of space-time with unique properties. In these distant, unobservable regions, fundamental constants, such as the speed of light, the strength of gravity, or the charges of particles, might differ from those in our own universe. Even small variations in these constants could lead to dramatically different physics, creating realms where familiar concepts like atoms, stars, and galaxies simply cannot exist. Such regions might host entirely novel structures, shaped by forces and interactions beyond our imagination. One way to conceptualize exotic physics is through the lens of higher dimensions. String theory, one of the leading candidates for a unified theory of everything, posits that the universe contains additional spatial dimensions beyond the three we experience. In our observable universe, these dimensions are thought to be compactified, folded so tightly that they are effectively invisible. However, in other parts of the cosmos, these dimensions might be larger or unfolded, creating environments with entirely different physical behaviors. For instance, in a universe with 4 spatial dimensions, gravity would behave very differently, weakening more rapidly with distance than it does in our 3-dimensional world. Such a change would have profound implications for the formation of stars, planets, and even life itself. Similarly, other universes might feature exotic particles or forces that are entirely absent from our own, shaping their structure and evolution in ways we can barely begin to comprehend. Another intriguing possibility is that exotic physics could arise from variations in the vacuum energy of spacetime. The vacuum, often thought of as empty, is in fact a seething field of quantum fluctuations, with particles popping in and out of existence. The energy density of this vacuum plays a critical role in determining the large-scale behavior of the universe, including its expansion rate. In regions where the vacuum energy differs, space-time might exhibit entirely different properties, creating realms where the familiar rules of physics break down. But how could we detect evidence of such exotic physics if these regions lie beyond our observational reach? One potential avenue is through the imprints they might leave on the observable universe. For example, if our region of the cosmos collided with another region governed by different physics, the resulting interaction could leave subtle distortions in the cosmic microwave background, CMB, the faint glow of radiation left over from the Big Bang. Similarly, gravitational waves, ripples in the fabric of space-time, could carry information about events in these exotic regions. If such waves pass through areas of space-time with different physical properties, they might be altered in ways that reveal clues about the conditions beyond our horizon. Advanced detectors, such as those operated by the Laser Interferometer Gravitational Wave Observatory, LIGO, may one day detect such anomalies, opening a window into the unseen cosmos. Another possibility is that exotic physics could manifest in regions closer to home, such as the interiors of black holes. Within a black hole, the known laws of physics break down at the singularity, a point of infinite density where space-time curvature becomes infinite. Some theories suggest that black holes might serve as gateways to regions of space-time governed by different laws, offering a glimpse of the exotic physics that might exist beyond our observable universe. Exotic physics also raises profound questions about the nature of reality itself. If the laws of physics vary across the cosmos, what determines the specific set of rules that govern our observable universe? Is it a matter of chance, the result of random fluctuations during cosmic inflation? Or is it the product of deeper, underlying principles that we have yet to uncover? These questions touch on the very foundations of cosmology, quantum mechanics, and the search for a unified theory of everything. One framework that seeks to address these questions is the multiverse hypothesis. In a multiverse, each universe could represent a different realization of the physical laws, with our universe being one of countless possibilities. This idea is often linked to the anthropic principle, which suggests that we observe the universe we do because it is one of the few, or the only one, capable of supporting life. While this explanation is controversial, it highlights the connection between exotic physics and the fundamental conditions for existence. The implications of exotic physics extend far beyond science. They challenge us to rethink our place in the cosmos, not as inhabitants of a single, isolated universe, but as part of a vast, interconnected reality filled with infinite possibilities. They invite us to explore the boundaries of human knowledge and imagination, pushing us to ask questions that transcend the limits of observation and experimentation. As we continue to explore the cosmos, the search for exotic physics will remain a driving force in our quest to understand the universe. Whether through theoretical models, advanced observations, or future technologies, the pursuit of this knowledge is a testament to the unyielding human desire to uncover the unknown. It reminds us that the cosmos is far more intricate, diverse, and extraordinary than we can ever fully comprehend. A boundless frontier that beckons us to dream, explore, and discover. Cosmic background radiation and hidden clues. The universe has left behind a faint but persistent whisper from its earliest moments, a cosmic fossil that holds the secrets of its origin and evolution. This is the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang. While this relic has illuminated much of our understanding about the observable universe, it also offers tantalizing hints about what lies beyond. Could the CMB contain hidden clues about unobservable realms, other universes, or the physics that shaped existence itself? The CMB was first discovered in 1964 by physicists Arno Penzias and Robert Wilson, who stumbled upon it while working on radio wave experiments. Initially confused by the faint, uniform hum of microwave radiation coming from all directions, they soon realized they had detected evidence of the universe's birth. The CMB, now measured at a temperature of about 2.7 Kelvin, minus 454.8 degrees Fahrenheit, is the thermal remnant of the Big Bang, stretched and cooled over billions of years by the universe's expansion. At its core, the CMB is a snapshot of the universe as it existed approximately 380,000 years after the Big Bang. Before this time, the cosmos was a hot, dense plasma where light could not travel freely, continuously scattering off charged particles. As the universe cooled, protons and electrons combined to form neutral atoms, allowing light to travel unimpeded for the first time. This decoupling of matter and radiation created the CMB, which has been traveling through space ever since. While the CMB appears uniform at first glance, detailed measurements reveal subtle temperature fluctuations, or anisotropies, across the sky. These fluctuations are the fingerprints of quantum density variations during cosmic inflation. Tiny differences that would later grow into galaxies, stars, and the large-scale structures of the universe. Studying these anisotropies has provided cosmologists with an incredible wealth of information, from the universe's age and composition to its rate of expansion. But what about the clues hidden within the CMB about regions beyond the observable universe? The CMB serves as a boundary for our observations, marking the furthest distance from which we can receive light. Beyond this surface of last scattering lies a time and space inaccessible to us, yet its imprints may be embedded in the CMB itself. One of the most intriguing anomalies in the CMB is the so-called cold spot, a region of the sky that is significantly cooler than surrounding areas. Discovered by NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite, the cold spot has defied explanation within standard cosmological models. Some theories suggest it could be a statistical fluke or the result of a massive supervoid, an enormous region of space with a lower-than-average density of matter. However, another explanation for the cold spot ventures into the realm of exotic physics. It could be evidence of a collision between our universe and another bubble universe in the multiverse. During cosmic inflation, if bubbles of space-time formed and expanded independently, occasional collisions might occur, leaving behind disturbances in the CMB. The cold spot, in this view, could be a scar from such a cosmic encounter, a tantalizing hint that our universe is not alone. Beyond anomalies like the cold spot, the CMB may also contain information about the universe's earliest moments. Patterns in the polarization of the CMB, specifically B modes, a type of swirling pattern, are believed to carry the imprint of primordial gravitational waves. These waves, ripples in space-time caused by violent events during inflation, could reveal insights into the physics of the very first fractions of a second of existence. If detected, these signals would offer a direct glimpse into the conditions that shaped not only our universe but potentially the multiverse as well. Another exciting avenue for uncovering hidden clues in the CMB involves its interaction with matter. As CMB photons travel through space, they encounter galaxy clusters, gravitational wells, and intergalactic gas. These interactions leave behind subtle effects, such as the Sunyaev-Zel'dovich (SZ) effect, where photons gain energy from hot gas in galaxy clusters, or the integrated Sachs-Wolf (ISW) effect, where photons are stretched by the expansion of spacetime. By studying these effects, astronomers can map the distribution of dark matter, understand the influence of dark energy, and explore the universe's large-scale structure. But the CMB's significance extends beyond what it reveals about the universe we can see. It also challenges us to confront the limitations of observation. While the CMB provides a detailed picture of the cosmos shortly after the Big Bang, it obscures what came before. The period known as the Dark Ages, before stars and galaxies formed, remains largely unexplored. Similarly, the conditions at the very beginning of the universe, during the Planck epoch, the first 10 to the power of -43 seconds, remain shrouded in mystery, hidden behind the veil of the CMB. The search for what lies beyond the CMB boundary has inspired novel approaches in cosmology. One such idea is the study of neutrinos, nearly massless particles that decoupled from matter even earlier than photons. These cosmic neutrino background particles could provide a glimpse into the universe mere seconds after the Big Bang. While detecting them is a monumental challenge due to their weak interactions with matter, future experiments may unlock this hidden layer of cosmic history. Similarly, gravitational waves hold the potential to peer beyond the CMB. Unlike light, gravitational waves are not scattered by matter, meaning they could carry information from the universe's earliest moments. Advanced detectors, such as those being developed by the Laser Interferometer Space Antenna, LISA, could one day reveal these primordial waves, offering unprecedented insights into the universe's birth. As we continue to study the CMB, its significance grows not only as a window into the observable universe, but as a gateway to the unseen. Its intricate patterns, subtle anomalies, and faint whispers of the past remind us that the cosmos is a vast and interconnected whole, with every photon of light carrying the story of creation. The CMB also serves as a humbling reminder of our place in the universe. It encapsulates the idea that while we may never fully uncover all the secrets of the cosmos, the pursuit of knowledge is itself a profound journey. Each discovery within the CMB deepens our appreciation for the universe's complexity, beauty, and boundless potential. As technology advances and our understanding of physics grows, the CMB will remain a cornerstone of cosmology, a map of the universe's past, and a key to unlocking its future. Whether it reveals clues about other universes, exotic physics, or the origins of existence, it stands as a testament to the power of human curiosity and the infinite possibilities that lie beyond the horizon. Gravitational waves and the unseen universe. Imagine the universe as a vast cosmic ocean. While light serves as the shimmering surface that reveals the shapes and colors of the cosmos, gravitational waves are like the ripples beneath, subtle, elusive, and carrying the echoes of unseen phenomena. These ripples in space-time, predicted by Einstein's theory of general relativity, have opened an entirely new window into the universe. But how can gravitational waves help us explore what lies beyond the observable horizon? Could they offer insights into the unobservable cosmos, or even clues about the nature of reality itself? Gravitational waves are distortions in space-time caused by the acceleration of massive objects, such as colliding black holes, merging neutron stars, or even the universe's earliest moments during cosmic inflation. These waves propagate outward at the speed of light, carrying information about the violent events that produce them. Unlike light, which can be blocked or scattered by matter, gravitational waves pass through everything, reaching us virtually unaltered. This makes them invaluable messengers, capable of revealing phenomena hidden from traditional telescopes. The detection of gravitational waves represents one of the most groundbreaking achievements in modern physics. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, announced the first-ever observation of gravitational waves, produced by the merger of two black holes. This discovery confirmed a key prediction of general relativity and launched a new era of astrophysics, enabling us to listen to the universe in ways never before possible. But gravitational waves are not limited to studying black holes and neutron stars. They also have the potential to unveil the secrets of the universe's hidden regions. One of the most exciting possibilities is the detection of primordial gravitational waves, ripples generated during the first moments of the Big Bang. These waves, if observed, would provide a direct glimpse into the Planck epoch, the first 10 to the power of -43 seconds of the universe's existence, when the known laws of physics break down. Such a discovery could offer critical insights into the processes that shaped the cosmos, including cosmic inflation and the potential existence of other universes. Primordial gravitational waves would carry imprints of the conditions beyond the observable universe. During inflation, quantum fluctuations in space-time were amplified to macroscopic scales, creating density variations that seeded the formation of galaxies. These fluctuations also produce gravitational waves, which would encode information about the regions of space-time inaccessible to us. By studying these waves, scientists could infer the properties of the unobservable cosmos, such as its curvature, dimensionality, and even its topology. Gravitational waves might also provide evidence for the multiverse. If our universe is one of many in a larger multiverse, interactions between universes could leave detectable traces in the form of gravitational waves. For instance, collisions between bubble universes during inflation would create shockwaves in space-time, producing unique gravitational wave signatures. Similarly, if space-time itself is shaped by higher dimensions, as suggested by string theory, gravitational waves could reveal their influence, offering clues about the structure of the cosmos beyond our horizon. Another intriguing possibility is the role of gravitational waves in studying dark matter and dark energy. Dark matter, the invisible substance that makes up about 27% of the universe, does not emit or absorb light, making it undetectable with traditional methods. However, gravitational waves could interact with dark matter, revealing its distribution and properties. Similarly, the accelerating expansion of the universe driven by dark energy might influence gravitational wave signals, providing insights into this mysterious force and its connection to the cosmos's hidden realms. Gravitational waves also challenge our understanding of black holes, some of the most enigmatic objects in the universe. When black holes collide, they produce powerful gravitational waves that carry information about their mass, spin, and the nature of their event horizons. But could black holes also serve as portals to other regions of space-time or even other universes? Some theories propose that black holes might connect to white holes, hypothetical regions where matter and energy are ejected rather than consumed, potentially linking our universe to others. Gravitational waves from such events could offer evidence for these exotic possibilities. The study of gravitational waves requires highly sophisticated technology. Detectors like LIGO and its European counterpart, Virgo, use laser interferometry to measure tiny changes in distance caused by passing waves, distortions as small as a fraction of the width of a proton. Future observatories, such as the Laser Interferometer Space Antenna, LISA, will operate in space, allowing for even more sensitive measurements over larger scales. These advancements will enable scientists to detect gravitational waves from more distant and lower frequency sources, including signals from the early universe. The potential of gravitational wave astronomy is vast. It allows us to probe phenomena that are otherwise invisible, from the interiors of black holes to the earliest moments of existence. It also complements other forms of observation, such as electromagnetic radiation and neutrinos, creating a more comprehensive picture of the cosmos. Yet, as we listen to the universe through gravitational waves, profound questions emerge. What does it mean to observe events that are inherently unseeable? How do these waves connect us to regions of space-time beyond our reach? And what do they reveal about the fundamental nature of reality? These questions remind us that the universe is not just a collection of stars and galaxies, but a dynamic, interconnected system, where even the faintest ripple carries meaning. Gravitational waves also highlight the interplay between science and imagination. While they are rooted in rigorous mathematics and observation, their implications push the boundaries of what we can conceive. They challenge us to think beyond the limitations of sight and embrace a more expansive view of the cosmos, one where every distortion in space-time is a story waiting to be told. As gravitational wave astronomy continues to evolve, it will undoubtedly uncover new mysteries and deepen our understanding of the universe's hidden dimensions. Whether it reveals the secrets of the multiverse, the origins of existence, or the nature of dark matter, it stands as a testament to the power of human curiosity and ingenuity. The ripples of space-time, once theoretical, are now a reality, a bridge connecting us to the unseen and inviting us to explore the infinite possibilities that lie beyond. Tachyons, wormholes, and faster-than-light travel. The universe is vast, and the observable cosmos is but a fraction of its true scale. Within the framework of current physics, the speed of light sets a hard limit on how far and how fast we can explore. But what if this limit could be surpassed? Concepts like tachyons, wormholes, and faster-than-light travel challenge the boundaries of known science, offering tantalizing possibilities for accessing regions of the universe beyond our observable horizon. Could these phenomena be the keys to uncovering what lies beyond? To begin, let's consider tachyons, hypothetical particles that could travel faster than light. First proposed in the 1960s, tachyons are rooted in the equations of special relativity. According to this theory, nothing with mass can accelerate to or beyond the speed of light without requiring infinite energy. However, tachyons, if they exist, would always move faster than light and would never slow down to subliminal speeds. The existence of tachyons would revolutionize our understanding of causality and space-time. For instance, their superluminal speeds could theoretically allow them to transmit information backward in time, violating one of the fundamental principles of physics. While no experimental evidence for tachyons has been found, their theoretical implications inspire exploration into realms of physics where faster-than-light phenomena might occur. If tachyons are speculative, wormholes offer a more grounded, albeit still theoretical, path to faster-than-light travel. A wormhole, or Einstein-Rosen bridge, is a solution to the equations of general relativity that describes a shortcut through space-time. Imagine folding a piece of paper so that two distant points touch. A wormhole would act as a tunnel connecting these points, allowing for instantaneous travel between them. Wormholes, if they exist, could connect not only distant parts of our own universe, but also entirely separate universes or regions beyond the observable horizon. These connections might make it possible to access parts of the cosmos that would otherwise remain forever out of reach, offering a direct path to the hidden realms of space-time. Some theories even suggest that traversable wormholes could be stabilized using exotic matter, a form of matter with negative energy density. However, wormholes come with significant challenges. First, they are inherently unstable, collapsing almost instantly without the presence of exotic matter to hold them open. Even if stabilized, they might be affected by quantum effects, potentially rendering them unusable for travel. Additionally, the immense gravitational forces near the mouth of a wormhole could pose significant risks to travelers or objects attempting to pass through. Faster-than-light travel is not just limited to tachyons and wormholes. The concept of a warp drive, popularized by science fiction, has gained serious attention in theoretical physics. Inspired by Einstein's equations, physicist Miguel Alcubierre proposed a model in 1994 for a warp drive that could compress space ahead of a spacecraft while expanding it behind. This would allow the craft to effectively ride a wave of space-time, moving faster than light relative to the surrounding universe without violating the laws of physics. The Alcubierre drive relies on the existence of negative energy or exotic matter to create the warp bubble. While such materials remain hypothetical, recent advances in quantum field theory and experiments with Casimir effects suggest that negative energy might be possible on small scales. If harnessed, this concept could provide a revolutionary means of exploring the universe, potentially reaching distant galaxies or even other universes within human lifetimes. Faster-than-light concepts also intersect with the idea of accessing higher dimensions. String theory, for instance, posits that additional spatial dimensions exist beyond the familiar three. If these dimensions could be manipulated, they might offer shortcuts through space-time, akin to wormholes but rooted in a higher dimensional framework. Such pathways could bypass the constraints of light-speed travel, enabling exploration of regions currently beyond reach. But faster-than-light travel raises profound questions about the nature of reality. If it were possible to traverse space-time at superluminal speeds, how would this affect our understanding of causality? Would time become a malleable concept, with events occurring out of sequence from different perspectives? Such questions challenge not only physics but also philosophy, forcing us to reconsider the fundamental structure of the universe. Despite their speculative nature, these concepts are not entirely without observational hints. For instance, some astrophysical phenomena, such as gamma-ray bursts and certain patterns in the cosmic microwave background, have been interpreted by a minority of scientists as potential evidence for exotic space-time structures. While these interpretations remain controversial, they highlight the ongoing search for phenomena that might point to faster-than-light physics. The search for faster-than-light travel is not just a scientific endeavor. It is a reflection of humanity's enduring curiosity and desire to transcend limits. The idea of exploring beyond the observable universe, of reaching the unreachable, captures the imagination and drives innovation. Even if concepts like tachyons, wormholes, and warp drives remain theoretical, their study pushes the boundaries of what we know and inspires new ways of thinking about the cosmos. As technology advances and our understanding of physics deepens, the dream of faster-than-light travel remains a beacon of possibility. Whether through the discovery of new particles, the manipulation of space-time, or the harnessing of exotic energy, the quest to transcend the speed of light reflects our drive to explore the infinite. It reminds us that the universe, vast and mysterious, is not a barrier, but an invitation, a frontier waiting to be crossed. Cosmic evolution and the distant future. As we delve deeper into the mysteries of the universe, it becomes clear that the cosmos is not a static entity. It is a dynamic, evolving system, shaped by time and driven by forces both known and unknown. But what does the future hold for the universe? How will cosmic evolution unfold in the eons to come? And what does it reveal about the hidden realms beyond our observable horizon? Exploring the distant future of the cosmos offers a glimpse into the ultimate fate of existence and the profound mysteries that await. To understand where the universe is headed, we must first examine its past and present. The story of cosmic evolution begins with the Big Bang, an event that marked the birth of space-time, matter, and energy approximately 13.8 billion years ago. In the aftermath of this explosion, the universe expanded rapidly, cooled, and formed the first atoms, stars, and galaxies. Over billions of years, gravity shaped these building blocks into the vast cosmic structures we observe today. At this moment, the universe is in its stelliferous era, a time dominated by star formation, galaxy evolution, and the interplay between dark matter, dark energy, and ordinary matter. Stars burn brightly, converting hydrogen into heavier elements through nuclear fusion, and galaxies interact, merge, and evolve. But this phase is temporary, a fleeting moment in the grand timeline of the cosmos. As we look to the future, the influence of dark energy becomes increasingly important. This mysterious force, which drives the accelerated expansion of the universe, will continue to push galaxies further apart. Over the next few billion years, the night sky as seen from Earth, or any other planet, will change dramatically. Distant galaxies will redshift beyond visibility, their light stretched to wavelengths too long to detect, leaving only the closest galaxies, such as Andromeda and the Milky Way, visible to future observers. This accelerated expansion has profound implications for the long-term fate of the cosmos. In one possible scenario, known as the Big Freeze, the universe will continue to expand indefinitely, becoming colder and darker over time. Star formation will eventually cease as galaxies exhaust their reserves of gas, leaving behind only remnants: white dwarfs, neutron stars, and black holes. These objects will persist for trillions of years, but even they are not eternal. On an even longer timescale, black holes, the ultimate gravitational powerhouses, will dominate the universe. Over billions of trillions of years, they will slowly evaporate through a process known as Hawking radiation, emitting faint streams of energy until they vanish completely. What remains is a universe filled with diffuse particles and radiation, a cold and desolate expanse known as heat death or the Big Chill. But is this the only possible future? Some theories suggest alternative outcomes, depending on the nature of dark energy and the ultimate shape of space-time. For instance, if dark energy's effects were to weaken or reverse, the universe could enter a phase of contraction, leading to a big crunch. In this scenario, galaxies and matter would collapse back into a singularity, potentially triggering another Big Bang, a cyclical view of cosmic evolution. Another possibility is the Big Rip, a dramatic scenario in which dark energy grows increasingly powerful over time. In this case, the expansion of the universe would accelerate to the point where galaxies, stars, planets, and even atoms are torn apart by the relentless force of dark energy. This cataclysmic end would leave the universe devoid of structure, a sea of particles separated by ever-growing distances. Cosmic evolution also raises questions about the fate of intelligent life. If civilizations survive long enough to witness these distant eras, how might they adapt to an aging universe? Advanced beings might develop technologies to harness energy from stars, black holes, or even the quantum vacuum itself. Some scientists have speculated about the possibility of creating artificial universes or escaping into higher dimensions to avoid the effects of cosmic decay. The distant future of the universe also has implications for what lies beyond the observable horizon. As galaxies recede and the cosmos becomes increasingly isolated, the unobservable regions of the universe will grow even more inaccessible. Yet, their influence on cosmic evolution persists, shaping the large-scale structure of space-time and potentially offering clues about the multiverse or exotic physics. Studying the future of the cosmos requires understanding the fundamental forces and particles that govern its behavior. Experiments in particle physics, such as those conducted at the Large Hadron Collider, LHC, aim to uncover the nature of dark matter, dark energy, and the ultimate fate of matter itself. These investigations could provide critical insights into the processes that will determine the universe's destiny. Cosmological simulations also play a key role in predicting the future. Using powerful supercomputers, scientists model the evolution of galaxies, black holes, and large-scale structures over billions of years, testing different scenarios based on current observations. These simulations help refine our understanding of how cosmic evolution unfolds and what the far future might hold. Despite its chilling implications, the study of cosmic evolution inspires awe and wonder. It reminds us that the universe is a dynamic, ever-changing entity, shaped by forces that span incomprehensible scales of time and space. It also highlights the resilience of life and intelligence, the ability to adapt, explore, and question even in the face of cosmic vastness. Ultimately, the distant future of the universe is a story of transformation. It is a reminder that while stars fade and galaxies drift apart, the quest for knowledge and understanding persists. As we explore the farthest reaches of time and space, we are not only uncovering the secrets of the cosmos, but also charting humanity's place within it. A fleeting moment in an infinite expanse, yet profoundly significant in its pursuit of the unknown. Alien civilizations beyond our view. When we look up at the night sky, we are greeted by a vast, silent expanse of stars and galaxies, each a potential host for life. Yet, for all our exploration and technological advancement, the universe has offered no definitive proof of alien civilizations. Could intelligent life exist beyond our observable horizon, hidden in the uncharted realms of the cosmos? If so, what might these civilizations be like, and how might they shape the universe in ways we cannot see? The search for extraterrestrial intelligence, or SETI, has long been a central focus of human curiosity. From early radio experiments to advanced space telescopes scanning distant planets, the effort to detect alien life has spanned decades. Yet, these efforts are limited by the boundaries of the observable universe, the finite region of space from which light has had time to reach us since the Big Bang. Beyond this horizon lie countless galaxies, star systems, and potentially habitable worlds, forever beyond our reach due to the constraints of light speed and cosmic expansion. Despite these limitations, the sheer scale of the universe suggests that alien civilizations could be abundant. The observable universe contains an estimated 200 billion galaxies, each home to hundreds of billions of stars and trillions of planets. If even a small fraction of these planets harbor life, the number of civilizations could be staggering. Beyond the observable horizon, this number grows exponentially, encompassing realms we will never see but can still imagine. To speculate about these civilizations, scientists often turn to the Kardashev scale, a framework for categorizing technological advancement based on energy consumption. A Type 1 civilization harnesses the energy resources of its home planet. A Type 2 civilization taps into the energy of its star, and a Type 3 civilization controls the energy of an entire galaxy. Humanity, by comparison, is still below Type 1, using only a fraction of Earth's available energy. Advanced civilizations beyond our horizon might have achieved Type 2 or even Type 3 status, reshaping their cosmic environments in ways we can scarcely comprehend. A Type 2 civilization, for example, might construct a Dyson sphere, a megastructure surrounding a star to capture its energy output. Such a structure would emit detectable infrared radiation, but if located beyond our horizon, it would remain invisible to us. A Type 3 civilization, meanwhile, could manipulate the energy of an entire galaxy, altering its dynamics or creating artificial structures on colossal scales. Such civilizations might even engage in intergalactic colonization, spreading their influence across vast cosmic distances. Yet, if these activities occur beyond the observable universe, they leave no trace in the data available to us. But how might alien civilizations communicate across such vast distances? Traditional radio signals are limited by the speed of light, making intergalactic communication incredibly slow. However, advanced technologies might exploit phenomena such as quantum entanglement, wormholes, or gravitational waves to transmit information instantaneously. These methods, while speculative, could allow civilizations to connect across the vast expanse of the cosmos, even linking regions beyond the observable universe. One intriguing possibility is that advanced civilizations might have already discovered ways to traverse the limits of the observable universe. Wormholes, if they can be stabilized, could serve as shortcuts through space-time, allowing travel between distant regions. Similarly, manipulation of higher dimensions, as proposed in string theory, might enable interuniversal travel. If such capabilities exist, alien civilizations could potentially bridge the gap between the observable and unobservable cosmos. The existence of civilizations beyond our horizon also raises profound philosophical questions. Are we alone, or is life a universal phenomenon? If life is common, why has it remained undetected? What some call the Great Silence. This paradox, often referred to as the Fermi paradox, has inspired countless hypotheses, from the idea that intelligent life self-destructs before achieving interstellar reach to the possibility that advanced civilizations intentionally avoid contact. One solution to the paradox is the notion of a cosmic quarantine, where advanced civilizations deliberately shield themselves from less developed ones, perhaps to avoid interference or contamination. If such civilizations exist beyond our horizon, their influence might shape the unobservable universe in ways we cannot perceive, creating vast enclaves of advanced life, communication networks, or artificial megastructures. Another possibility is that civilizations beyond our view operate on timescales so vast that their activities are invisible to us. Galactic-scale projects, such as moving stars or engineering black holes, might unfold over millions or billions of years, rendering them imperceptible to short-lived species like humanity. Such civilizations might regard the universe itself as a canvas for creation, reshaping its structure and laws according to their needs. Despite the lack of direct evidence, the search for alien civilizations continues to inspire scientific and philosophical inquiry. Missions like the James Webb Space Telescope aim to study the atmospheres of exoplanets for signs of life, while radio telescopes like FAST in China and the SETI Institute's Allen Telescope Array scan the skies for signals from distant civilizations. These efforts are confined to the observable universe, but they provide a foundation for imagining what lies beyond. As we ponder the existence of alien life, it is worth considering the potential implications for humanity. The discovery of intelligent civilizations, whether within or beyond our horizon, would forever alter our understanding of our place in the cosmos. It would challenge us to think beyond Earth-centric perspectives, to consider the vast diversity of life and intelligence that the universe might host. Ultimately, the question of alien civilizations beyond our view is a reminder of the universe's boundless possibilities. Whether they exist as distant neighbors, creators of cosmic megastructures, or guardians of hidden realms. Their potential presence inspires us to look outward, to seek answers, and to dream of what might be. In the infinite expanse of the cosmos, the search for life is not just a scientific endeavor. It is a journey into the heart of existence itself. The nature of infinity, concept or reality. Infinity is a concept that has fascinated humanity for millennia, stretching our minds beyond the limits of comprehension. In mathematics, philosophy, and science, it challenges the very framework of thought, suggesting a realm where the rules we rely on may no longer apply. But what does infinity mean in the context of the universe? Is it merely an abstract idea, or could it be a fundamental feature of reality? As we venture beyond the observable cosmos, the nature of infinity emerges as a profound question with far-reaching implications. To understand infinity, we must first consider its role in mathematics. Infinity often represents a quantity without end, a number larger than any conceivable value. It appears in simple concepts like the endless series of numbers, and in more complex constructs, such as limits in calculus or the uncountable infinities described by set theory. These mathematical infinities are abstract, existing only within the realm of thought, yet they have profound implications for our understanding of the physical world. In cosmology, the concept of infinity takes on a more tangible form. One of the central questions about the universe is whether it is finite or infinite in extent. If the universe is infinite, it implies an endless expanse of space, filled with stars, galaxies, and other structures stretching forever. This notion challenges our ability to grasp the true scale of existence, raising questions about what infinity means in a physical sense. The observable universe, as vast as it is, represents only a finite region of the cosmos. It is defined by the cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang. Beyond this horizon lies the unobservable universe, which may extend indefinitely. If the cosmos is infinite, then our observable universe is merely a tiny bubble in an endless sea of space, with no boundaries or edges. But how can we determine whether the universe is truly infinite? Observational evidence provides some clues. Measurements of the cosmic microwave background, CMB, the large-scale distribution of galaxies, and the curvature of space-time all suggest that the universe is flat or nearly flat. A flat universe, according to the principles of geometry, could be infinite in extent. However, it is also possible for a flat universe to be finite but unbounded, looping back on itself like the surface of a torus or a higher-dimensional structure. If the universe is infinite, it carries profound implications for the nature of existence. For example, in an infinite cosmos, every possible configuration of matter must exist somewhere. This idea, known as the cosmic doppelganger hypothesis, suggests that there could be an infinite number of galaxies identical to our own, each containing identical Earths with identical versions of ourselves. This notion, while unsettling, is a natural consequence of infinity combined with the laws of probability. Infinity also raises questions about time. Does time extend infinitely into the past and future? Or did it have a beginning and will it have an end? The Big Bang Theory suggests that time began approximately 13.8 billion years ago, coinciding with the creation of space-time itself. However, some theories propose that our universe is part of an eternal cycle of expansion and contraction, with no beginning or end. In this view, infinity is not a feature of space alone, but of time as well. The concept of infinity is also central to the multiverse hypothesis. If our universe is one of many in a multiverse, the total number of universes could be infinite. These universes might vary in size, age, and physical laws, creating a vast metacosmos beyond our comprehension. In this context, infinity takes on a new dimension, representing not just the endlessness of space, but the boundless possibilities of existence itself. Yet, the idea of infinity is not without its challenges. In physics, infinities often signal a breakdown in our understanding. For instance, the singularities at the centers of black holes, or at the beginning of the Big Bang, represent points where density and curvature become infinite, rendering current theories of space-time inadequate. These infinities suggest the need for new physics, perhaps a quantum theory of gravity, to resolve the paradoxes they create. Philosophically, infinity poses profound questions about the nature of reality. Is infinity a fundamental feature of the universe, or is it a construct of the human mind? Does the concept of infinity exist independently of observation, or is it a convenient way to describe phenomena that surpass our ability to measure? These questions challenge the boundaries of science and philosophy, highlighting the interplay between thought and reality. The nature of infinity also inspires reflection on humanity's place in the cosmos. If the universe is infinite, our observable region is an infinitesimal fraction of the whole, a humbling reminder of our smallness in the grand scheme of existence. Yet, within this infinite context, every individual moment and experience takes on extraordinary significance, representing a unique expression of the cosmos's boundless potential. Exploring infinity requires not only theoretical inquiry, but also practical observation. Advances in cosmology, such as deep field surveys, gravitational wave detection, and studies of the cosmic microwave background, continue to refine our understanding of the universe's structure and extent. Meanwhile, mathematical research into the nature of infinity, such as the work of George Cantor and his successors, provides a foundation for interpreting its physical implications. Ultimately, the question of whether infinity is a concept or a reality may remain unresolved. Yet, its exploration is a testament to the human spirit, a drive to push beyond the limits of understanding, to seek answers to questions that defy easy resolution. Infinity is more than a number or an idea. It is a window into the profound mysteries of the universe, an invitation to explore the endless possibilities of existence. As we peer into the cosmos, the infinite beckons, challenging us to expand our minds and embrace the unknown. Whether as a mathematical construct, a physical reality, or a philosophical enigma, infinity remains a cornerstone of our quest to understand the universe, a reminder that the journey of discovery is itself endless, as vast and boundless as the cosmos it seeks to comprehend. The role of quantum entanglement in exploring the unknown. Quantum entanglement, a phenomenon described by Albert Einstein as spooky action at a distance, is one of the most perplexing and fascinating concepts in modern physics. It defies classical intuition, suggesting that particles can be connected in ways that transcend the limits of space and time. But how might quantum entanglement play a role in exploring the unknown regions of the universe, including realms beyond the observable cosmos? Could this mysterious connection between particles offer a key to unlocking the secrets of the hidden universe? To understand quantum entanglement, we must first delve into the basics of quantum mechanics. At its core, quantum mechanics describes the behavior of particles on the smallest scales: atoms, electrons, and photons. Unlike classical objects, quantum particles exist in a state of superposition, simultaneously representing multiple possibilities until measured. When two particles interact, their quantum states can become entangled, meaning their properties become interdependent, regardless of the distance between them. The entanglement between particles is so profound that measuring the state of one particle instantly determines the state of its partner, even if they are separated by light years. This instantaneous connection has been experimentally confirmed, challenging our understanding of causality and the speed of information transfer. While entanglement does not allow for faster-than-light communication, it suggests that the universe is deeply interconnected in ways that defy classical explanations. The implications of entanglement for exploring the unknown are vast. One of the most intriguing possibilities is its potential to reveal information about regions beyond the observable universe. If particles in our universe are entangled with particles in distant, unobservable realms, their behavior could carry subtle imprints of these hidden regions. By studying the correlations between entangled particles, scientists might infer properties of the cosmos that lie beyond the reach of light. Entanglement also plays a critical role in the development of quantum technologies, such as quantum computers and quantum networks. These technologies have the potential to revolutionize our ability to process and transmit information, enabling unprecedented levels of precision in cosmological studies. For example, quantum sensors could detect minute gravitational waves or fluctuations in spacetime, offering insights into phenomena occurring in distant or hidden regions of the universe. One of the most exciting frontiers in quantum research is the idea of quantum teleportation. While teleportation does not involve physically moving particles across space, it allows the quantum state of a particle to be transmitted to another particle at a different location, using entanglement as a bridge. This process has been successfully demonstrated in laboratory settings, and its potential applications for cosmology are profound. For instance, quantum teleportation could enable the transfer of information across vast cosmic distances, bridging gaps between observable and unobservable regions. Quantum entanglement also intersects with the study of black holes and the nature of space-time. In recent years, physicists have proposed that entanglement might be the key to understanding the information paradox of black holes, a puzzle about how information escapes from black holes despite their intense gravitational pull. Some theories suggest that entanglement connects particles on opposite sides of a black hole's event horizon, creating a bridge known as an Einstein-Rosen bridge, or wormhole. If true, entanglement could be the foundation for understanding how space-time itself is structured. Beyond black holes, entanglement may have implications for the fabric of the universe at the most fundamental level. Some theories propose that space-time is not a continuous entity, but emerges from a network of quantum entanglements, a concept known as quantum gravity. In this view, the geometry of the universe is a manifestation of the underlying entanglement between particles, linking even the most distant regions of the cosmos. Entanglement also challenges our understanding of locality, the idea that objects can only influence their immediate surroundings. If particles can remain entangled across vast distances, it suggests that the universe operates on principles that transcend classical notions of space and time. This interconnectedness raises profound questions about the nature of reality and our place within it. Despite its potential, harnessing entanglement for cosmological exploration remains a significant challenge. Entangled states are fragile, easily disrupted by interactions with their environment, a phenomenon known as decoherence. Overcoming this limitation requires advances in quantum technology and a deeper understanding of how entanglement operates on large scales. Yet, even in its current form, entanglement offers a tantalizing glimpse into the hidden workings of the universe. The philosophical implications of quantum entanglement are as profound as its scientific ones. If the universe is interconnected at a quantum level, what does this mean for the nature of individuality and separation? Are we, as conscious beings, fundamentally connected to the cosmos in ways we cannot perceive? These questions echo ancient philosophical ideas about the unity of existence, suggesting that modern physics is converging with timeless insights. Entanglement also serves as a reminder of the universe's complexity and mystery. It challenges us to think beyond the boundaries of classical physics, to embrace a worldview that is dynamic, interconnected, and deeply non-intuitive. It invites us to explore the unknown, not just as observers, but as participants in a vast, entangled cosmos. As we continue to study quantum entanglement, its role in understanding the universe will only grow. Whether it reveals hidden dimensions, connects us to regions beyond our horizon, or unlocks the secrets of space-time, entanglement stands as a testament to the power of human curiosity and imagination. It reminds us that the universe is not just a collection of stars and galaxies, but a deeply interconnected web, where every particle, every event, and every moment is part of a larger cosmic whole. Simulation hypothesis. Is the universe a hologram? As we continue to explore the mysteries of the universe, one question stands out as particularly provocative. What if everything we see, feel, and experience is not the ultimate reality, but a simulation? The simulation hypothesis suggests that our universe might be an artificial construct, created by an advanced intelligence, or perhaps even by ourselves in the far future. This idea challenges our perception of reality, offering a radical framework for understanding the cosmos and what might lie beyond. The origins of the simulation hypothesis can be traced to philosophy, particularly the works of René Descartes, who questioned the reliability of our senses and the nature of existence. However, it was Swedish philosopher Nick Bostrom who formalized the concept in 2003 with his seminal paper, Are you living in a computer simulation? Bostrom argued that if advanced civilizations eventually develop the technology to create highly realistic simulations, it is statistically more likely that we are living in one of those simulations than in the original base reality. At the core of the hypothesis is the idea that reality as we perceive it may be a vast computational construct. Just as video games simulate entire worlds with virtual characters and environments, an advanced civilization could theoretically simulate a universe down to its fundamental particles and forces. This simulated universe would be indistinguishable from real reality to those inside it, meaning we might never know we're in a simulation. But how does this relate to the cosmos? If the universe is a simulation, it implies that everything we observe, from the stars and galaxies to the fundamental laws of physics, is part of the simulation's code. The observable universe, with its vastness and complexity, could be a construct designed to appear natural, following consistent rules and patterns to sustain the illusion of reality. One of the most compelling arguments for the simulation hypothesis lies in the nature of physical laws. The universe operates according to mathematical principles, with constants and equations that govern everything from the behavior of subatomic particles to the motion of galaxies. This mathematical consistency has led some physicists to speculate that the universe might be akin to a computational system, with physical laws serving as the programming code. Moreover, certain features of a universe resemble those of a digital simulation. For instance, the Planck scale, the smallest measurable units of space and time, could be interpreted as the pixel resolution of the universe, akin to how digital images and simulations have finite resolutions. Similarly, quantum mechanics, with its probabilistic nature, might represent the random number generation used in simulations to model uncertainty. If the universe is a simulation, what lies beyond? One possibility is that our universe is embedded in a larger, more complex reality, the hardware or platform running the simulation. This meta-universe could be vastly different from our own, governed by entirely different principles and hosting beings or entities far more advanced than we can imagine. If our universe is one of many simulations, these simulated realities might interact in subtle ways, leaving imprints on our cosmos. The simulation hypothesis also raises questions about the motivations of the creators. Why simulate a universe? One possibility is scientific curiosity. Advanced civilizations might simulate universes to study their origins, test theories, or explore alternate scenarios. Another possibility is entertainment. Simulations might be created for leisure, much like how humans create video games and virtual reality experiences. Alternatively, simulations could serve as a form of preservation, with beings seeking to encode their consciousness or culture into a virtual reality to escape the physical limits of their original existence. Testing the simulation hypothesis is an extraordinary challenge, but some scientists have proposed intriguing experiments. For example, physicists have suggested that if the universe is a simulation, it might exhibit computational limits or anomalies, such as unexplained deviations in physical constants or inconsistencies in cosmic background radiation. Others have speculated that advanced simulations might include glitches or artificial signatures that could be detected with sufficiently sensitive instruments. Quantum mechanics might also offer clues. The phenomenon of quantum entanglement, where particles remain connected across vast distances, could hint at underlying computational processes linking distant parts of the simulation. Similarly, the probabilistic nature of quantum events might reflect the algorithmic behavior of the simulation's code. If we are in a simulation, what happens if it ends? This question evokes deep existential concerns. Just as humans can pause or delete virtual worlds, the creators of a simulated universe might have the power to terminate or modify it. However, from the perspective of those within the simulation, the end might be indistinguishable from natural cosmic phenomena, such as a big crunch or a phase transition in space-time. The philosophical implications of the simulation hypothesis are profound. If reality is a simulation, it challenges our understanding of free will, existence, and purpose. Are we autonomous beings, or are our thoughts and actions predetermined by the simulation's programming? Does meaning exist in a simulated reality, or is it an illusion? These questions resonate with age-old philosophical debates about the nature of consciousness and reality. Yet, the hypothesis also offers a sense of wonder. If the universe is a simulation, it suggests that existence is deeply interconnected, designed with intention and purpose. It also implies that the boundaries of reality are not fixed but can be transcended, perhaps even by those within the simulation. Advanced civilizations within a simulation might discover ways to interact with or escape into the meta-reality, breaking free from the confines of their virtual world. Whether or not the universe is a simulation, the hypothesis encourages us to think beyond conventional boundaries. It invites us to question the nature of reality, to explore the mysteries of existence, and to embrace the unknown. In doing so, it reflects the core of scientific and philosophical inquiry, a relentless pursuit of understanding, driven by curiosity and imagination. Ultimately, the simulation hypothesis is not just a question of whether we live in a simulated universe. It is an exploration of what it means to exist, to perceive, and to create. It challenges us to confront the deepest mysteries of the cosmos and to wonder about the infinite possibilities that lie beyond the limits of our understanding. Black holes and hidden realms. Few phenomena in the universe are as mysterious and awe-inspiring as black holes. These regions of space-time, where gravity is so intense that nothing, not even light, can escape, have long captured the imagination of scientists and the public alike. But black holes are more than just cosmic curiosities. They may hold the key to understanding the universe's most hidden realms. Could they serve as gateways to other dimensions, bridges between universes, or portals to regions beyond the observable cosmos? To understand the enigmatic nature of black holes, we must first explore their formation and structure. Black holes are created when massive stars exhaust their nuclear fuel and collapse under their own gravity. This collapse compresses the star's core into a singularity, a point of infinite density where space-time curves infinitely and the known laws of physics break down. Surrounding the singularity is the event horizon, a boundary beyond which nothing can escape. While the event horizon marks the edge of a black hole's influence, its interior is a region of profound mystery. According to Einstein's general relativity, the singularity at a black hole's core represents a breakdown of space-time itself. However, quantum mechanics suggests that this singularity might not be the end of the story. Instead, it could be a gateway to phenomena that lie outside our current understanding, including connections to other parts of the universe, or even other universes. One of the most tantalizing ideas in theoretical physics is that black holes might be linked to white holes. A white hole is the hypothetical opposite of a black hole, a region of space-time that ejects matter and energy but cannot be entered. If black holes and white holes are connected, they could form a tunnel through space-time known as a wormhole. Such a wormhole might allow for faster-than-light travel or even access to regions beyond the observable universe. Wormholes, or Einstein-Rosen bridges, were first proposed as a solution to Einstein's equations of general relativity. While they remain speculative, their mathematical foundations suggest that black holes could serve as the entrance points to these cosmic shortcuts. If stabilized, a wormhole could provide a pathway between distant regions of space, or between entirely separate universes in a multiverse. However, stabilizing a wormhole would likely require exotic matter with negative energy density, a concept that, while theoretically possible, has yet to be observed. Black holes also challenge our understanding of information and the nature of reality. The information paradox arises from the question of what happens to the information about the matter and energy that falls into a black hole. According to quantum mechanics, information cannot be destroyed, yet it seems to vanish when it crosses the event horizon. Resolving this paradox has led to revolutionary ideas, such as the holographic principle, which suggests that all the information within a black hole might be encoded on its two-dimensional event horizon. The holographic principle has profound implications for the nature of the universe itself. If information can be stored on a two-dimensional surface, it raises the possibility that our three-dimensional reality might be a projection of information encoded on a higher dimensional boundary. This idea, often described as the universe being a hologram, could explain how black holes preserve information while also hinting at the fundamental structure of space-time. Black holes may also serve as laboratories for exploring quantum gravity, the elusive theory that seeks to unify general relativity and quantum mechanics. At the heart of this quest is the understanding that the extreme conditions near a black hole's event horizon push the boundaries of both classical and quantum physics. By studying these environments, physicists hope to uncover the underlying principles that govern the universe at its most fundamental level. One intriguing possibility is that black holes might connect to higher dimensional realms. In string theory, which posits the existence of additional spatial dimensions, black holes could act as funnels, linking our four-dimensional space-time to these hidden dimensions. Such connections might offer explanations for phenomena like dark matter or provide insights into the structure of the multiverse. Black holes also have practical implications for understanding the unobservable universe. Their immense gravitational influence affects the motion of nearby stars and gas, offering clues about the distribution of matter beyond our horizon. Observations of supermassive black holes at the centers of galaxies, such as Sagittarius A** in the Milky Way, reveal how these objects shape the evolution of galaxies and cosmic structures. Recent technological advancements, such as the Event Horizon Telescope, EHT, have provided unprecedented views of black holes. In 2019, the EHT captured the first-ever image of a black hole's event horizon, a glowing ring of light surrounding the dark shadow of the singularity. These observations offer direct evidence of black holes' existence and open new doors for studying their properties. Despite these breakthroughs, many questions remain. Are black holes truly singularities, or do they harbor exotic states of matter? Do they connect to other regions of space-time? And if so, can these connections be traversed? And what role do they play in the larger structure of the universe? These mysteries inspire ongoing research and theoretical exploration. Beyond their scientific significance, black holes provoke profound philosophical questions. They challenge our notions of space, time, and causality, suggesting that reality is far stranger than it appears. They also highlight the universe's dual nature, a realm of order governed by predictable laws, yet filled with enigmas that defy understanding. Ultimately, black holes are more than just cosmic anomalies. They are windows into the unknown, portals to the boundaries of science and imagination. Whether they serve as gateways to other universes, repositories of hidden information, or engines of cosmic transformation, their study offers a glimpse into the deepest mysteries of existence. In their shadows, we find not just the limits of light, but the limitless possibilities of discovery. The role of mathematics in predicting the beyond. Mathematics is often described as the language of the universe, a framework that allows us to decode the cosmos's deepest mysteries. From the laws of motion to the structure of space-time, mathematical equations have consistently predicted phenomena far before they were observed. But how does mathematics help us explore realms beyond the observable universe? Can it illuminate the hidden corners of reality and provide a glimpse into the uncharted territories that lie beyond our reach? To understand the power of mathematics in cosmology, consider its history of predictive success. In the 19th century, French mathematician Urbain Le Verrier used mathematical calculations to predict the existence of Neptune based on irregularities in Uranus's orbit. His prediction was later confirmed through direct observation. In the 20th century, Albert Einstein's equations of general relativity predicted the existence of black holes and gravitational waves, concepts that seemed fantastical at the time but have since been validated by experiments and observations. The predictive power of mathematics lies in its ability to describe patterns and relationships that transcend specific contexts. Equations like the Friedmann-Lemaitre, Robertson-Walker, FLRW metric, which describes the expansion of the universe, provide insights into its structure, evolution, and ultimate fate. These mathematical models are not limited by the constraints of observation. They allow us to explore scenarios far beyond what we can directly measure. One of the most significant ways mathematics aids in predicting the beyond is through models of cosmic inflation. The equations governing inflation describe how the universe expanded exponentially in its earliest moments, smoothing out irregularities and creating the conditions for the large-scale structures we see today. These models also suggest the existence of unobservable regions of the universe, shaped by quantum fluctuations during inflation. By refining these equations, physicists can infer properties of the cosmos that lie beyond our observable horizon. Mathematics also plays a central role in the multiverse hypothesis. Theoretical frameworks such as string theory and eternal inflation suggest that our universe is one of countless others, each with its own unique properties. While these other universes are inherently unobservable, mathematical models describe their potential existence and behavior. For example, the equations governing bubble collisions in a multiverse could leave imprints in the cosmic microwave background, providing indirect evidence of these hidden realms. Another area where mathematics shines is in the study of higher dimensions. String theory posits that the universe consists of more than the three spatial dimensions we experience, with additional dimensions compactified at tiny scales. These extra dimensions, though invisible, influence the behavior of particles and forces in our universe. Mathematical tools like Calabi-Yau manifolds describe the shapes and structures of these dimensions, offering insights into how they might connect to the observable world. Mathematics also predicts phenomena that challenge our understanding of reality. The discovery of dark energy, the mysterious force driving the accelerated expansion of the universe, was rooted in mathematical models of cosmic dynamics. Similarly, the existence of dark matter, inferred from discrepancies in the motion of galaxies and galaxy clusters, relies on mathematical analyses of gravitational effects. These predictions highlight how mathematics can reveal unseen components of the cosmos, guiding the search for new physics. One of the most exciting frontiers in mathematical cosmology is the quest for a unified theory of everything, a single framework that reconciles general relativity with quantum mechanics. These two pillars of modern physics describe the universe on vastly different scales, but their incompatibility suggests the need for a deeper, underlying theory. Mathematics is at the heart of this search, with equations like the Schrödinger equation, Einstein's field equations, and the principles of quantum field theory providing clues to the nature of spacetime. The predictive power of mathematics extends to the ultimate fate of the universe. By analyzing the interplay of dark energy, dark matter, and ordinary matter, mathematical models describe scenarios such as the Big Freeze, Big Rip, and Big Crunch. These equations not only predict how the universe might evolve, but also hint at what might lie beyond, whether in the form of a cyclic universe, a transition to a new phase of existence, or a connection to other universes. Mathematics also challenges us to think beyond the limits of human intuition. Concepts like infinity, higher dimensions, and non-Euclidean geometry stretch the boundaries of imagination, providing tools to explore ideas that defy everyday experience. For instance, the idea of an infinite universe emerges naturally from mathematical models of space-time geometry, while the equations of quantum mechanics suggest the existence of parallel realities in the form of the many worlds interpretation. But mathematics is not without its philosophical implications. Does the universe follow mathematical laws because it is inherently mathematical, or is mathematics simply a human construct that happens to describe reality effectively? This question, known as the unreasonable effectiveness of mathematics, has intrigued philosophers and scientists for decades. If the universe is fundamentally mathematical, it raises profound questions about the nature of existence and the role of consciousness in perceiving it. Mathematics also confronts us with the limits of knowledge. Gödel's incompleteness theorems, for instance, demonstrate that no mathematical system can be both complete and consistent, suggesting that there will always be truths about the universe that lie beyond formal proof. Similarly, the Heisenberg uncertainty principle in quantum mechanics imposes fundamental limits on our ability to measure certain properties of particles, highlighting the interplay between mathematical precision and physical reality. Despite these challenges, mathematics remains an indispensable tool for exploring the unknown. Advances in computational power and numerical simulations allow scientists to solve equations that were once intractable, revealing new insights into the behavior of galaxies, black holes, and the early universe. These tools also enable the exploration of speculative ideas, such as the nature of singularities, the behavior of spacetime at the Planck scale, and the potential for time travel. Ultimately, the role of mathematics in predicting the beyond is a testament to its power and universality. It bridges the gap between the observable and the unobservable, providing a framework to explore the deepest mysteries of the cosmos. Whether describing the motion of planets, the formation of galaxies, or the structure of spacetime itself, mathematics is a guide, a language that allows us to peer into the unknown and imagine the infinite. As we continue to push the boundaries of knowledge, mathematics will remain at the forefront of discovery. It is a reminder that the universe, in all its complexity, is not just a collection of objects and events, but a deeply interconnected system, governed by patterns and relationships that transcend the physical. In the language of mathematics, we find not only the keys to the cosmos, but a reflection of the boundless potential of the human mind, cosmic strings, and higher dimensions. As we delve deeper into the mysteries of the universe, one of the most fascinating and speculative ideas emerges from the intersection of cosmology and theoretical physics: the existence of cosmic strings and their potential connection to higher dimensions. These theoretical structures, remnants of the universe's earliest moments, could offer profound insights into the fabric of space-time and the hidden realms beyond the observable cosmos. But what exactly are cosmic strings, and how might they relate to dimensions beyond our perception? The nature of cosmic strings. Cosmic strings are hypothesized to be ultra-thin, one-dimensional defects in space-time, formed during the early universe's rapid cooling following the Big Bang. Similar to cracks that form in ice as water freezes, these strings are thought to have arisen as the universe transitioned through different states, creating topological defects in the fabric of space-time. They are incredibly dense, with a single string stretching across the universe potentially weighing as much as an entire galaxy. Unlike the strings in string theory, which are microscopic and fundamental, cosmic strings are macroscopic, potentially spanning vast distances. Their gravitational effects would be immense, capable of bending space-time around them. This warping of space-time could produce phenomena such as gravitational lensing, where light from distant stars and galaxies is bent as it passes near a cosmic string, creating multiple images or distortions of the same object. Detecting cosmic strings. Despite their theoretical appeal, cosmic strings remain elusive, as no direct evidence of their existence has been found. However, scientists have proposed several ways to detect them. One method involves searching for the gravitational waves they might produce. As cosmic strings vibrate and reconnect, they could release bursts of gravitational waves, ripples in space-time that could be detected by advanced observatories like LIGO and Virgo. Another avenue involves studying the cosmic microwave background, CMB, the faint glow of radiation left over from the Big Bang. Cosmic strings could leave subtle imprints in the CMB, such as temperature fluctuations or distinctive patterns that deviate from standard cosmological models. These clues could provide indirect evidence of their presence and offer insights into the early universe's dynamics. Cosmic strings and the structure of space-time. The existence of cosmic strings has profound implications for our understanding of space-time. Because they represent defects in the fabric of the universe, they hint at the possibility that space-time itself is not smooth and continuous, but has a more complex, underlying structure. This idea aligns with theories of quantum gravity, which suggest that space-time at the smallest scales may be granular or composed of discrete units. Cosmic strings could also act as probes for exploring the nature of higher dimensions. In theories like string theory and M-theory, the universe is thought to contain additional spatial dimensions beyond the familiar three. These dimensions are typically compactified, curled up at scales too small to observe, but their effects could manifest through phenomena like cosmic strings. For instance, strings might serve as conduits or bridges between higher dimensional spaces and our observable universe, revealing glimpses of these hidden realms. The connection to higher dimensions. Higher dimensions are a cornerstone of string theory, which posits that the fundamental building blocks of the universe are tiny, vibrating strings that operate in a multidimensional space-time. While we perceive only 3 spatial dimensions and 1 temporal dimension, string theory suggests the existence of up to 11 dimensions, with the extra dimensions influencing the properties of particles and forces. Cosmic strings might provide a way to test these ideas. If strings are connected to higher dimensional structures, they could exhibit behaviors that deviate from predictions based on standard four-dimensional physics. For example, a cosmic string moving through a higher dimensional space might produce unique gravitational effects or interact with dark matter and dark energy in unexpected ways. One particularly intriguing possibility is that cosmic strings could form loops or networks that extend into higher dimensions. These loops might oscillate, releasing energy in the form of gravitational waves or other signals that could be detected by future experiments. Such observations would provide direct evidence of the connection between cosmic strings and higher dimensional physics, offering a glimpse into the hidden architecture of the universe. Cosmic strings and the multiverse. The idea of cosmic strings also intersects with the concept of the multiverse. In some models of cosmic inflation, the rapid expansion of space-time after the Big Bang created not just one universe, but many, each with its own physical laws and properties. Cosmic strings, as relics of these inflationary processes, might serve as markers of interactions between different universes. For instance, if two bubble universes collided during inflation, the impact could create a network of cosmic strings at the boundary between them. These strings would preserve information about the collision, acting as cosmic fossils of events that occurred beyond our observable horizon. Studying such strings could provide indirect evidence of the multiverse and offer clues about the nature of these hidden realms. Implications for the observable universe. Even within our observable universe, cosmic strings could play a significant role in shaping its structure and evolution. Their immense gravitational pull could influence the formation of galaxies and large-scale cosmic structures, acting as seeds for the clustering of matter. By studying their potential effects, scientists can refine their models of how the universe evolved from its earliest moments to its current state. Cosmic strings also challenge our understanding of causality and the flow of time. Because they warp space-time so intensely, they could create closed time-like curves, pathways through space-time that loop back on themselves, theoretically allowing for time travel. While highly speculative, this possibility highlights the profound implications of cosmic strings for our understanding of physics. The future of cosmic string research. Advances in technology and observation are bringing us closer to uncovering the secrets of cosmic strings. Next-generation gravitational wave detectors, such as the Laser Interferometer Space Antenna, LISA, will have the sensitivity to detect the faint signals produced by vibrating strings. Similarly, upcoming surveys of the cosmic microwave background, such as those conducted by the Simons Observatory and CMB-S4, will provide more detailed maps of the early universe, potentially revealing the signatures of cosmic strings. Theoretical research is also expanding our understanding of how cosmic strings might interact with other components of the universe, such as dark matter, dark energy, and black holes. These studies could uncover new connections between strings and the fundamental forces of nature, deepening our understanding of the cosmos. Cosmic strings as a bridge to the beyond. Ultimately, cosmic strings represent a bridge between the known and the unknown, connecting the physics of the observable universe to the mysteries of higher dimensions and the multiverse. They challenge us to think beyond conventional boundaries, to explore the hidden structure of space-time, and to imagine the infinite possibilities of existence. As we continue to study these theoretical objects, they remind us that the universe is not just a vast collection of stars and galaxies, but a deeply interconnected system, shaped by forces and phenomena that transcend our understanding. In the quest to uncover the secrets of cosmic strings, we are not just exploring the universe. We are venturing into the very fabric of reality itself. Technological frontiers in observing the unknown. As humanity reaches deeper into the cosmos, the tools and technologies we use to study the universe are evolving at an unprecedented pace. From groundbreaking telescopes to revolutionary particle detectors, these advancements are pushing the boundaries of observation and allowing us to explore realms once thought inaccessible. What are the cutting-edge technologies that promise to unlock the secrets of the universe? And how might they help us uncover the mysteries beyond the observable horizon? Next-generation space telescopes. Telescopes have long been our eyes on the cosmos, and the next generation of space-based observatories promises to revolutionize our understanding of the universe. One of the most anticipated is the James Webb Space Telescope, JWST, already delivering unparalleled insights into the early universe. Its infrared capabilities allow it to peer through cosmic dust and observe the first galaxies and stars that formed after the Big Bang, shedding light on the universe's infancy. Following JWST, projects like the Nancy Grace Roman Space Telescope will provide a wide-field view of the cosmos, enabling precise measurements of dark energy and the large-scale structure of the universe. The Roman telescope's ability to map billions of galaxies will enhance our understanding of cosmic expansion and offer clues about regions beyond our observable horizon. Even further on the horizon are telescopes like LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and HABEX, Habitable Exoplanet Observatory. These proposed missions aim to search for Earth-like planets around distant stars and analyze their atmospheres for signs of life. By studying exoplanets in detail, they may help answer the age-old question of whether life exists elsewhere in the cosmos, potentially even beyond our visible universe. Gravitational wave observatories. Gravitational waves, ripples in space-time caused by massive cosmic events, have opened an entirely new way of observing the universe. The Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo detectors have already detected waves from merging black holes and neutron stars, confirming Einstein's predictions and revealing previously hidden phenomena. Next-generation observatories like LISA, Laser Interferometer Space Antenna, will extend this capability by operating in space, where they can detect lower-frequency gravitational waves. These signals, produced by supermassive black hole mergers, or even the universe's earliest moments, could provide insights into the nature of space-time and the conditions beyond the observable universe. Gravitational wave astronomy also offers a unique way to study dark matter, cosmic strings, and other exotic phenomena. By analyzing the waveforms of these ripples, scientists can probe the universe's hidden components, uncovering clues about its unseen structure. Cosmic microwave background studies. The cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang, is one of the most valuable sources of information about the universe's early history. Current observatories like the Planck satellite have provided detailed maps of the CMB, revealing patterns that reflect the distribution of matter and energy shortly after the Big Bang. Future CMB missions, such as the Simons Observatory and CMB S4, will take this research to new levels of precision. By studying the polarization of the CMB, these observatories aim to detect the faint imprints of primordial gravitational waves, which would offer direct evidence of cosmic inflation and insights into the conditions beyond our observable horizon. Particle accelerators and detectors. On Earth, particle accelerators like the Large Hadron Collider, LHC, at CERN are probing the universe's smallest components. By smashing particles together at nearly the speed of light, the LHC has uncovered fundamental particles such as the Higgs boson, deepening our understanding of the forces that govern the cosmos. The next generation of particle accelerators, including proposals like the Future Circular Collider, FCC, aims to explore even higher energy scales. These experiments could reveal new particles, confirm the existence of extra dimensions, or uncover the nature of dark matter and dark energy. Such discoveries would transform our understanding of the universe and its hidden realms. In addition to accelerators, neutrino detectors like IceCube in Antarctica are exploring the cosmos in unique ways. Neutrinos, nearly massless particles that rarely interact with matter, carry information about distant and extreme cosmic events. By studying their behavior, scientists hope to trace their origins to supernovae, black holes, or other exotic sources. Radio astronomy and fast radio bursts. Radio astronomy continues to be a vital tool for exploring the universe, offering insights into phenomena invisible to optical telescopes. The discovery of fast radio bursts, FRBs, brief, intense flashes of radio waves, has added a new layer of mystery to the cosmos. While their origins remain uncertain, some FRBs may be tied to exotic astrophysical events or even advanced alien civilizations. Facilities like the Square Kilometre Array, SK, currently under construction, will revolutionize radio astronomy. The SK's immense sensitivity and resolution will enable it to map the universe's large-scale structure, study dark energy, and investigate the origins of FRBs. It may also help detect signals from extraterrestrial intelligence, further expanding our cosmic perspective. Quantum technologies and space exploration. Quantum technologies are poised to play a transformative role in cosmology. Quantum sensors, based on principles like superposition and entanglement, offer unparalleled precision in detecting gravitational waves, dark matter, and other elusive phenomena. These sensors could enable breakthroughs in understanding the universe's most fundamental components. Space exploration technologies are also advancing rapidly. Missions like Breakthrough Starshot, which aims to send tiny, light-powered spacecraft to nearby stars, could revolutionize interstellar exploration. These probes, traveling at a fraction of the speed of light, might gather data from distant regions of the galaxy, offering a closer look at planetary systems beyond our solar system. Artificial intelligence and data analysis. The sheer volume of data generated by modern observatories and experiments is staggering, far exceeding the capacity of traditional analysis methods. Artificial intelligence, AI, and machine learning are becoming essential tools for processing and interpreting this data. From identifying exoplanets in telescope images to finding patterns in gravitational wave signals, AI is accelerating discoveries and uncovering connections that might otherwise go unnoticed. AI also has the potential to assist in hypothesis generation, exploring vast parameter spaces to propose new models of the universe. By simulating scenarios beyond the observable cosmos, AI could help refine our understanding of phenomena like cosmic inflation, dark matter, and the multiverse. The quest to observe the unobservable. While current technologies offer remarkable capabilities, they are still limited by the constraints of observation. The speed of light, cosmic expansion, and the opacity of the early universe create barriers that prevent us from directly observing regions beyond our cosmic horizon. However, indirect methods such as studying gravitational waves, neutrinos, or quantum phenomena provide pathways to explore the unseen. Ultimately, the technological frontiers of cosmology reflect humanity's unyielding curiosity and drive to explore the unknown. As we develop ever more sophisticated tools, we move closer to answering profound questions about the nature of the universe, its origins, and its ultimate fate. Each new discovery deepens our understanding, pushing the boundaries of knowledge and inspiring future generations to continue the journey. In the quest to observe the unobservable, we are not merely building machines. We are crafting bridges to the infinite, opening windows to the cosmos's hidden realms and revealing the extraordinary tapestry of existence that lies beyond our reach. The intersection of consciousness and the cosmos. Among the many mysteries of the universe, one question stands out as both profoundly personal and deeply scientific. What is the nature of consciousness, and how does it relate to the cosmos? While consciousness is typically viewed as a phenomenon rooted in the human brain, its implications extend far beyond biology. Could consciousness be a fundamental aspect of the universe itself, woven into the fabric of space-time? And if so, what role does it play in understanding the cosmos and the realms beyond our observable horizon? The nature of consciousness. Consciousness is often described as the subjective experience of awareness, the ability to perceive, think, and feel. While its mechanisms are studied in neuroscience, its origins and nature remain elusive. Is consciousness merely the result of complex neural processes, or does it arise from more fundamental principles? This question has sparked debates across disciplines, from physics to philosophy. The concept of panpsychism posits that consciousness might not be exclusive to biological entities, but could be a fundamental property of the universe. In this view, even the most basic components of matter, such as atoms and subatomic particles, might possess rudimentary forms of awareness. If true, consciousness would be as intrinsic to the cosmos as gravity or electromagnetism, potentially playing a role in the evolution of the universe itself. Quantum mechanics and consciousness. One of the most intriguing connections between consciousness and the cosmos lies in quantum mechanics. The observer effect, the idea that the act of observation influences the behavior of quantum particles, has led some to speculate about the role of consciousness in shaping reality. In experiments like the double-slit experiment, particles such as electrons behave differently when observed, collapsing from a wave-like state of probabilities into a definite state. While the observer effect is often attributed to the interaction of measurement devices rather than consciousness itself, the phenomenon raises profound questions about the nature of reality and the relationship between mind and matter. Could consciousness play a role in determining the universe's structure, influencing events at the quantum level? Or is it merely an emergent property of the physical processes governed by quantum laws? The anthropic principle and the role of observers. The anthropic principle suggests that the universe's physical laws and constants appear finely tuned to support life and consciousness. If even a single constant, such as the strength of gravity or the charge of the electron, were slightly different, the universe might not support stars, planets, or life as we know it. This apparent fine-tuning has led some to propose that consciousness is not merely a byproduct of the universe, but a central feature. One interpretation of the anthropic principle is that the universe is structured in a way that allows conscious observers to emerge and reflect upon its nature. In the context of a multiverse, where countless universes with varying physical laws exist, consciousness might arise only in universes where the conditions are just right. This idea links the emergence of conscious beings to the larger structure of reality, suggesting that observers are integral to the cosmos. Consciousness and the simulation hypothesis. The simulation hypothesis, discussed earlier, posits that the universe might be a computational construct created by an advanced intelligence. In this context, consciousness could be analogous to software running on the hardware of the simulated cosmos. If the universe is a simulation, consciousness might be a deliberate feature, designed to interact with and explore the simulated environment. Alternatively, consciousness itself could be the driving force behind the simulation. Some theorists propose that advanced civilizations might create simulations to explore the nature of consciousness, testing how it arises and evolves under different conditions. In this view, the cosmos could be a grand experiment in understanding the interplay between mind and matter. Cosmological implications of consciousness. If consciousness is a fundamental aspect of the universe, it could have profound implications for our understanding of cosmic evolution. For instance, some theories suggest that the universe might be a self-organizing system, with consciousness playing a role in guiding its development. This idea aligns with the concept of the participatory universe, proposed by physicist John Archibald Wheeler, who argued that observers help shape the universe through their interactions with it. Consciousness might also influence the nature of time and space. In some interpretations of quantum mechanics, the act of observation collapses probabilistic states into definite outcomes, effectively creating reality. If consciousness has a similar effect on the fabric of space-time, it could play a role in shaping the universe's structure and dynamics, potentially influencing phenomena beyond the observable cosmos. The search for consciousness beyond Earth. The study of consciousness extends beyond humans to the search for extraterrestrial life. If consciousness is a universal phenomenon, it might manifest in forms vastly different from those we know. Advanced civilizations, if they exist, could possess forms of consciousness that transcend biology, existing as artificial intelligence, collective minds, or even as entities integrated with space-time itself. The discovery of extraterrestrial consciousness would revolutionize our understanding of the cosmos and our place within it. It would challenge the anthropocentric view of intelligence and highlight the diversity of ways in which awareness might emerge and evolve across the universe. Bridging science and philosophy. The exploration of consciousness bridges the gap between science and philosophy, prompting questions that challenge the limits of empirical observation. What is the relationship between the mind and the physical universe? Does consciousness exist independently of matter, or is it an emergent property of complex systems? These questions invite interdisciplinary approaches, combining insights from neuroscience, physics, and metaphysics. Some frameworks, such as integrated information theory, IIT, attempt to quantify consciousness by measuring the complexity of a system's informational processes. Others, like orchestrated objective reduction, OR, proposed by physicists Roger Penrose and Stuart Hameroff, suggest that consciousness arises from quantum processes within the brain. While these theories differ in their details, they reflect a growing effort to understand consciousness as both a scientific and cosmic phenomenon. Consciousness and the infinite. The relationship between consciousness and infinity is another area of profound speculation. If the universe is infinite, does consciousness have the potential to expand infinitely as well? Could advanced beings explore infinite dimensions of thought and experience, transcending the limits of time and space? These questions touch on the intersection of cosmology, spirituality, and the nature of existence itself. Some philosophical traditions suggest that consciousness and the universe are deeply intertwined, with the cosmos serving as a reflection of the mind. In this view, exploring the universe is a way of exploring consciousness, and vice versa. This perspective resonates with the idea that the cosmos is not just a physical realm, but a profound mystery that invites reflection and self-discovery. The future of consciousness studies. As technology advances, the study of consciousness is poised to enter a new era. Brain-computer interfaces, artificial intelligence, and virtual reality are providing tools to investigate the nature of awareness and its relationship to the physical world. These technologies could help unlock the mysteries of how consciousness arises, evolves, and interacts with the cosmos. The exploration of consciousness is not just a scientific endeavor, but a deeply personal and existential one. It reminds us that the quest to understand the universe is also a quest to understand ourselves. In the interplay between mind and matter, we find not just the keys to the cosmos, but the essence of what it means to exist, the boundless potential of awareness. Ultimately, the intersection of consciousness and the cosmos challenges us to expand our vision of reality. It invites us to explore the universe, not just as observers, but as participants in a grand, interconnected system. Whether consciousness is a byproduct of matter, a fundamental aspect of space-time, or a bridge to higher dimensions, its mysteries remind us of the boundless potential of human curiosity and imagination. In seeking to understand consciousness, we are not just probing the nature of the universe. We are exploring the very essence of existence, unveiling a reality that is as infinite and interconnected as the cosmos itself. The universe is a hologram, implications and mysteries. Among the most profound and perplexing ideas in modern physics is the holographic principle, a concept suggesting that the universe might be a vast, multidimensional projection, much like a hologram. While the term evokes science fiction imagery, the principle is rooted in cutting-edge theoretical physics and mathematics, offering a revolutionary way to think about the nature of reality. Could the universe itself be a holographic construct? And if so, what does that mean for the mysteries of existence, including what lies beyond our observable horizon? Origins of the holographic principle. The holographic principle emerged from attempts to reconcile quantum mechanics with general relativity, particularly in the context of black hole physics. In the 1970s, physicist Stephen Hawking discovered that black holes emit radiation, now known as Hawking radiation, and eventually evaporate. This finding led to the information paradox, a conflict between quantum mechanics, which holds that information cannot be destroyed, and the apparent loss of information in black holes. In the 1990s, physicists Leonard Susskind and Gerard T. Hoof proposed a solution. The information about everything that falls into a black hole is not lost, but encoded on its event horizon, the two-dimensional surface surrounding the black hole. This idea suggested that the three-dimensional interior of the black hole could be fully described by data on its two-dimensional boundary. The holographic principle generalizes this concept, proposing that the entire universe may similarly be encoded on a two-dimensional surface. How does a holographic universe work? In a holographic universe, all the information that defines our three-dimensional reality, stars, galaxies, planets, and even the flow of time, might be stored on a two-dimensional boundary at the edge of the universe. This boundary acts like a cosmic hard drive, encoding the physics of everything within the universe. Our perception of three-dimensional space and time would then be a projection of this encoded information, much like a holographic image projected from a two-dimensional surface. The mathematics of string theory, particularly in the context of the anti-de Sitter/conformal field theory, ADS/CFT correspondence, provides a framework for understanding this concept. ADS/CFT, formulated by physicist Juan Meldacena in 1997, demonstrates a duality between a higher dimensional gravitational theory and a lower dimensional quantum field theory. In essence, It suggests that a universe with gravity can be equivalent to a lower-dimensional universe without gravity, offering a mathematical foundation for the holographic principle. Evidence for a holographic universe. While the holographic principle is primarily a theoretical construct, there are hints that it might reflect reality. One line of evidence comes from the study of black holes and their entropy. The Bekenstein-Hawking entropy formula reveals that the amount of information a black hole can store is proportional to the area of its event horizon, not its volume. This supports the idea that information in the universe could be encoded on two-dimensional surfaces. Another intriguing clue comes from observations of the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Some researchers have suggested that subtle patterns in the CMB might be consistent with a holographic model of the universe, though these interpretations remain speculative. Experiments designed to test the holographic principle are also underway. For instance, the holometer experiment at Fermilab aims to detect holographic noise, tiny fluctuations in spacetime that might result from the universe's underlying two-dimensional structure. While results are inconclusive, such experiments highlight the growing effort to probe the holographic nature of reality. Implications for understanding the universe. If the universe is indeed a hologram, it challenges many of our assumptions about space, time, and reality. For one, it suggests that the three-dimensional world we experience is not fundamental, but emergent, a macroscopic manifestation of deeper, more abstract principles encoded on a two-dimensional surface. This perspective also reshapes how we think about causality and locality. In a holographic universe, events separated by vast distances might be interconnected at a fundamental level, with the information encoding them stored in the same underlying framework. This could help explain quantum entanglement, where particles influence each other instantaneously across great distances, defying classical notions of cause and effect. The holographic principle also offers potential insights into the nature of spacetime. If spacetime itself is a projection, its apparent smoothness might be an illusion, masking a more granular, quantum structure. This idea aligns with theories of quantum gravity, which suggest that spacetime at the smallest scales is not continuous, but consists of discrete units. What lies beyond the holographic horizon? In a holographic universe, the observable horizon, the maximum distance from which light has had time to reach us since the Big Bang, takes on new significance. This horizon might represent a boundary where the two-dimensional encoding of our reality transitions to something entirely different. Beyond this boundary could lie other holographic projections, alternate realities, or the meta-universe from which our hologram emerges. The concept of a holographic universe also intersects with the multiverse hypothesis. If each universe in a multiverse is a holographic projection, then the surface encoding our universe might be part of a larger, interconnected system of surfaces, each representing a distinct reality. These connections could offer pathways for information transfer or even travel between universes, though such ideas remain highly speculative. Philosophical and existential questions. The holographic principle raises profound philosophical questions about the nature of existence. If reality is a projection, what does it mean to exist? Are we, as conscious beings, part of the projection, or do we have some connection to the underlying framework? These questions echo ancient philosophical ideas, such as Plato's allegory of the cave, where perceived reality is likened to shadows on a wall, mere reflections of a deeper truth. The holographic principle also challenges our understanding of meaning and purpose. If the universe is a projection, does it imply design, intention, or artistry? Or is it the result of natural processes governed by mathematical laws? These questions invite reflection not only on the nature of the cosmos, but on our place within it. The future of holographic research. As theoretical and experimental physics advances, the holographic principle may move from speculation to a cornerstone of our understanding of the universe. New discoveries in quantum gravity, black hole physics, and cosmology could provide further evidence for this radical idea. At the same time, advances in technology, such as quantum computing and artificial intelligence, might offer tools to simulate and test holographic models. Ultimately, the holographic principle is more than a scientific hypothesis. It is a window into the profound mysteries of existence. It challenges us to think beyond the limits of perception and imagination, to explore the interconnectedness of all things, and to embrace the possibility that reality itself is far more intricate and extraordinary than it appears. The fate of the universe. Scenarios beyond the observable horizon. The cosmos is a dynamic, evolving entity, and as we study its past and present, we inevitably turn to its ultimate fate. Will the universe continue expanding forever, or will it collapse back into itself? Could it transition into a new state, or perhaps cycle through infinite iterations? These questions are not just about the observable universe, but touch on the nature of existence beyond the cosmic horizon. By examining the leading scenarios for the universe's future, we can glimpse the profound mysteries of what lies beyond. The Big Freeze, eternal expansion. One of the most widely accepted scenarios for the fate of the universe is the Big Freeze, in which the universe continues to expand indefinitely. This idea is supported by observations of dark energy, the mysterious force driving the accelerated expansion of space-time. As galaxies are pushed further apart, the density of matter and energy decreases, leading to a cold, dark, and desolate cosmos. In the Big Freeze scenario, star formation will gradually cease as galaxies exhaust their supply of gas. Existing stars will burn out, leaving behind remnants such as white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will fade, leaving a universe filled with sparse particles and radiation. Beyond the observable horizon, this expansion would have profound implications. Regions of space currently beyond our view might also experience similar fates, with the fabric of space-time stretching infinitely. If the universe is infinite, the Big Freeze would leave it in a state of eternal stillness, a cold, featureless expanse that extends forever. The Big Rip, the end of space-time. A more dramatic possibility is the Big Rip, in which dark energy's influence grows stronger over time. If the energy density of dark energy increases, it could overcome all other forces, tearing apart galaxies, stars, planets, and even atoms. In this scenario, space-time itself would be destroyed, ending the universe in a catastrophic rupture. The Big Rip raises fascinating questions about the unobservable cosmos. If space-time disintegrates, what becomes of the regions beyond our horizon? Could they remain intact, governed by different physical laws or dark energy dynamics? Alternatively, the destruction of space-time in one region might trigger the birth of a new universe elsewhere, linking the Big Rip to the concept of cosmic rebirth. The Big Crunch, a cyclical universe. The opposite of the Big Freeze is the Big Crunch, in which the expansion of the universe slows, stops, and reverses. Under this scenario, gravity eventually overcomes dark energy, pulling galaxies back together. The universe would collapse into a singularity, potentially triggering another Big Bang. A cyclical universe model, where the Big Bang and Big Crunch alternate in infinite cycles, has intrigued scientists and philosophers alike. In this view, the cosmos undergoes eternal rebirth, with each iteration producing a new version of reality. Beyond our observable horizon, this cyclical process might play out on an infinite scale, with countless parallel universes existing simultaneously in various stages of expansion and contraction. The Big Bounce, a quantum perspective. The Big Bounce scenario combines elements of the Big Crunch with principles of quantum mechanics. It suggests that as the universe collapses, quantum effects prevent it from reaching a true singularity. Instead, the collapsing universe bounces back, creating a new phase of expansion. The Big Bounce aligns with certain theories of quantum gravity, such as loop quantum cosmology, which posits that space-time is discrete rather than continuous. In this framework, the universe's rebirth is not just a reset, but a continuation, with information from the previous phase influencing the next. This raises intriguing possibilities for what might lie beyond our observable horizon. If the universe is cyclic, regions we cannot see today could re-emerge in future iterations, connected through the bounce. Vacuum decay, a quantum catastrophe. Another potential fate of the universe is vacuum decay, a phenomenon rooted in quantum field theory. In this scenario, the universe's current state, a false vacuum, could transition to a lower-energy true vacuum. This transition would occur via quantum tunneling, creating a bubble of true vacuum that expands at the speed of light, annihilating everything in its path. Vacuum decay is particularly chilling because it could happen at any moment without warning. Beyond our observable horizon, the process might already be underway, with expanding bubbles of true vacuum altering the structure of space-time. If our universe is one of many in a multiverse, vacuum decay might cascade across universes, reshaping the landscape of reality itself. Heat death, the ultimate entropy. The concept of heat death is tied to the second law of thermodynamics, which states that entropy, or disorder, increases over time. In this scenario, the universe reaches a state of maximum entropy, where all energy is evenly distributed and no processes can occur. This state represents the ultimate thermodynamic equilibrium, a universe devoid of life, structure, and activity. Heat death is often associated with the Big Freeze, as both involve the universe cooling and fading over time. Beyond the observable horizon, heat death implies a uniformity that extends infinitely, with no variation or possibility for renewal. However, some theories suggest that quantum fluctuations could still occur in this state, potentially seeding the birth of new universes. Implications for the unobservable universe. While these scenarios describe the fate of the observable universe, they also have profound implications for the unobservable regions of the cosmos. If the universe is infinite, its ultimate fate might differ across regions, with some areas experiencing heat death while others undergo renewal. Alternatively, the unobservable universe might remain unaffected by processes in our region, existing in a state beyond our comprehension. The multiverse hypothesis adds another layer of complexity. If our universe is one of many, its fate might be just one chapter in an ongoing cosmic narrative. Other universes could continue to thrive, interact, or influence each other, creating a dynamic metacosmos that transcends the boundaries of any single reality. Philosophical and existential reflections. The fate of the universe raises profound questions about the nature of existence and our place within it. If the cosmos is destined for decay or destruction, what does that mean for the meaning and value of life? Conversely, if the universe is eternal and cyclical, how do we reconcile the infinite nature of time with our finite experiences? These questions invite reflection on the interconnectedness of life and the cosmos. Whether the universe ends in a big freeze, big rip, or another scenario, its story is also our story, an expression of the same fundamental principles that give rise to stars, galaxies, and consciousness. The role of observation and theory. Advancing our understanding of the universe's fate requires both observational breakthroughs and theoretical innovation. Projects like the Euclid satellite, the Dark Energy Spectroscopic Instrument DESI, and next-generation gravitational wave detectors will refine our knowledge of dark energy, cosmic expansion, and the universe's large-scale structure. At the same time, advancements in quantum gravity, string theory, and multiverse models will provide deeper insights into the forces shaping the cosmos. Ultimately, the study of the universe's fate is a journey into the unknown, a quest to understand not just where we are headed, but what lies beyond the observable horizon. In exploring these scenarios, we are not merely predicting the end. We are expanding the boundaries of human knowledge, embracing the infinite possibilities of existence, and finding meaning in the vast, interconnected tapestry of the cosmos. The role of dark matter and dark energy in shaping the unknown. The universe is a masterpiece of complexity, and yet most of it remains hidden. Dark matter and dark energy, two mysterious components of the cosmos, comprise the vast majority of its total mass energy. While neither can be directly observed, their influence is profound, shaping the evolution of galaxies, the expansion of space-time, and potentially even the fate of the universe. But how do these enigmatic entities help us understand the unobservable regions of the cosmos? Could they offer clues about the realms beyond our reach? The dark side of the universe. Dark matter and dark energy are not just esoteric concepts. They are necessary components of the standard model of cosmology, known as the Lambda-CDM model. Observations suggest that ordinary matter, the atoms that make up stars, planets, and living beings, accounts for only about 5% of the universe. Dark matter constitutes approximately 27%, while dark energy dominates at 68%. Despite their prevalence, the true nature of these entities remains elusive. Dark matter does not emit, absorb, or reflect light, making it invisible to traditional telescopes. Its presence is inferred from its gravitational effects, such as the motion of stars within galaxies and the bending of light around massive objects, a phenomenon known as gravitational lensing. Dark energy, on the other hand, is even more enigmatic. Discovered through the observation of the accelerating expansion of the universe, dark energy acts as a repulsive force, counteracting gravity on cosmic scales. Its properties suggest it is uniform across space-time, influencing the universe's structure and evolution in ways that defy understanding. Dark matter, the hidden framework. Dark matter serves as the invisible scaffolding of the universe, providing the gravitational pull necessary for galaxies to form and remain stable. Without it, the observed rotation speeds of stars within galaxies would be impossible to explain. Its influence extends beyond individual galaxies to the cosmic web, a vast network of filaments and voids that defines the large-scale structure of the universe. But what is dark matter? Leading candidates include weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. These hypothetical particles interact weakly with ordinary matter, making them difficult to detect. Experiments like Xenon 1T, the Large Hadron Collider, and direct detection searches aim to identify these particles, offering a window into the hidden components of the cosmos. If dark matter extends beyond our observable universe, it could play a key role in shaping regions we cannot see. Its gravitational influence might govern the formation of galaxies and clusters in unobservable areas, creating structures that mirror or differ from those within our horizon. Dark energy, the driver of expansion. Dark energy's influence became apparent in the late 1990s, when astronomers discovered that distant supernovae were dimmer than expected, indicating that the universe's expansion is accelerating. This revelation upended traditional cosmology, suggesting that a previously unknown force is driving the acceleration. Dark energy is often modeled as a cosmological constant, a term originally introduced by Einstein to describe a static universe. However, it could also represent a dynamic field, such as quintessence, which evolves over time. Alternatively, dark energy might be a manifestation of new physics, such as extra dimensions or modifications to general relativity. Beyond the observable universe, dark energy's role becomes even more intriguing. If the cosmos is infinite, dark energy might drive regions beyond our view into an accelerated expansion, separating them from our own universe. This cosmic isolation would render vast portions of the cosmos forever unreachable, hidden not just by the speed of light, but by the relentless expansion of space-time. The intersection of dark matter and dark energy. While dark matter and dark energy are often studied separately, their interplay is crucial to understanding the universe's evolution. Dark matter's gravitational pull counteracts dark energy's repulsion, shaping the formation of galaxies, clusters, and the cosmic web. This delicate balance determines the universe's large-scale structure and its ultimate fate. In regions beyond our observable horizon, the relative dominance of dark matter and dark energy might vary, creating environments with different physical laws or structures. Such variations could offer clues about the multiverse or reveal deeper principles underlying the cosmos. Dark matter and dark energy beyond the horizon. The unobservable universe, regions of space-time too distant for light to have reached us, presents a unique challenge for cosmology. However, the effects of dark matter and dark energy might offer indirect insights into these hidden realms. For example, the distribution of dark matter within the observable universe provides hints about the underlying structure of space-time. By studying gravitational lensing, galaxy clustering, and the motion of galaxies, scientists can infer patterns that extend beyond the visible horizon. These patterns might reveal whether the universe is truly homogeneous on large scales, or whether variations exist that could point to unobservable phenomena. Dark energy, too, could hold secrets about the cosmos beyond our reach. If it varies over time or space, it might create regions of the universe with different expansion rates or physical properties. These differences could manifest in the behavior of distant galaxies or the cosmic microwave background, providing clues about the nature of spacetime itself. Theoretical implications and new physics. The study of dark matter and dark energy has profound implications for fundamental physics. If dark matter is composed of particles beyond the standard model, their discovery would revolutionize our understanding of matter and forces. Similarly, if dark energy arises from quantum fields, it could reveal new principles of energy and space-time. Some theories suggest that dark matter and dark energy might be connected. For instance, certain models propose that dark matter particles interact with dark energy fields, influencing cosmic expansion. Others suggest that dark energy might arise from the vacuum energy of spacetime, linking it to the quantum realm. In the context of the multiverse, dark matter and dark energy might vary between universes, creating a diverse landscape of realities. Such variations could explain why our universe has the specific properties that allow for galaxies, stars, and life to exist, a question often framed by the anthropic principle. Observational frontiers. Advancing our understanding of dark matter and dark energy requires cutting-edge technology and innovative approaches. Upcoming projects, such as the Euclid Satellite, the Vera C. Rubin Observatory, and the Nancy Grace Roman Space Telescope, aim to map the distribution of dark matter and measure the effects of dark energy with unprecedented precision. Gravitational wave observatories like LISA and neutrino detectors, like IceCube, may also provide new ways to probe these mysterious components of the universe. By combining observations across multiple wavelengths and scales, scientists hope to unravel the connections between dark matter, dark energy, and the unobservable cosmos. Philosophical implications. The dominance of dark matter and dark energy in the universe raises profound philosophical questions. Why is most of the universe hidden from view? Does this hidden reality reflect deeper principles about the nature of existence? Or is it simply a consequence of the universe's physical laws? These questions challenge us to rethink our place in the cosmos, embracing the idea that the visible world is just a small part of a vast and mysterious whole, toward a unified understanding. As we continue to study dark matter and dark energy, their role in shaping the cosmos becomes increasingly clear. These hidden components not only govern the structure and evolution of the observable universe, but also hint at the nature of regions beyond our reach. By unlocking their secrets, we move closer to understanding the fundamental forces that define reality itself. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.